Hello there, and welcome to Science for Sleep, the quiet little corner of the universe where curiosity slows down, questions stretch out comfortably, and science takes the scenic route toward rest. Tonight's journey begins with a telescope, a daring idea, and a patch of sky that, at first glance, appeared to contain absolutely nothing at all. Not a bright star, not a swirling nebula, not even a faint smudge of distant light, just darkness. Yet that darkness, as it turns out, was hiding one of the most astonishing discoveries in modern astronomy, a discovery that quietly reshaped how scientists think about the universe itself. So wherever you happen to be listening from tonight, perhaps curled up under a blanket, perhaps drifting towards sleep after a long day, I'd love to ask a small question before we begin. Where in the world are you right now, and what time is it there? Maybe it's late evening, when the outside world grows quieter and the mind begins to wander. Maybe it's early morning somewhere across the globe, with the sky just beginning to brighten. Or maybe it's the middle of the night when the stars are doing their best work, scattered across the darkness above. It's a funny thing, really. This little moment we share right now exists in thousands of different time zones at once, each listener arriving here at a slightly different point in their own day. Yet somehow we're all meeting in the same story, and tonight's story begins with the Hubble Space Telescope staring into what looked like empty space. If you find this slow journey through the cosmos soothing, or simply enjoy winding down with a little gentle science before sleep, feel free to give the video a like and maybe subscribe to the channel. It helps this quiet little corner of the internet reach others who might also appreciate a calm moment beneath the stars. But for now, there's nothing you need to do except settle in, relax your thoughts a little, and let the universe unfold at its own unhurried pace. Because the moment we're about to explore began with a surprisingly simple question. What happens if you point one of the most powerful telescopes ever built at nothing? To understand why that question mattered, we have to travel back to the early 1990s, when the Hubble Space Telescope was still a relatively new arrival in orbit. Hubble, as many people know, circles Earth far above the atmosphere. Roughly 540 kilometers above the ground, it glides around the planet every 90 minutes, moving fast enough to stay in orbit while quietly watching the cosmos. Up there, the telescope avoids one of the biggest problems that ground-based observatories face: Earth's atmosphere. From the surface of our planet, starlight has to pass through layers of air before reaching a telescope. Those layers swirl and shift constantly, bending the light slightly as it travels. The result is that stars appear to twinkle, which is charming when you're looking up with your eyes, but rather inconvenient when you're trying to study distant galaxies with extreme precision. Hubble, floating above that turbulent air, gets a far clearer view. Its mirror, measuring 2.4 meters across, gathers light that has traveled for millions or even billions of years before finally arriving at the telescope's instruments. Cameras mounted behind that mirror record incredibly detailed images of distant cosmic objects. At least that was the plan. When Hubble first launched in 1990, something unexpected happened. Shortly after the telescope began sending its first images back to Earth, scientists noticed a problem. The pictures were blurry. Not hopelessly blurry, but blurry enough to be frustrating. After years of planning and billions of dollars spent on development, it turned out that Hubble's main mirror had a tiny flaw in its shape. The error was so small that it measured just 2 micrometers, roughly 1/50th the width of a human hair. But in the precise world of optics, that tiny mistake was enough to scatter incoming light in the wrong way. Instead of the crisp cosmic images astronomers had hoped for, the telescope produced slightly smeared pictures of stars and galaxies. For a while, it seemed like the most expensive pair of glasses in history had been built with the wrong prescription. Fortunately, engineers and astronauts came up with a clever solution. In 1993, a team aboard the Space Shuttle Endeavour carried out one of the most complex repair missions ever attempted in orbit. During several long spacewalks, astronauts installed corrective optics inside Hubble, essentially giving the telescope a set of contact lenses designed to fix the mirror's flaw. When the upgraded telescope began sending images back to Earth again, the difference was astonishing. Suddenly, the universe snapped into focus. Stars appeared as sharp points of light. Galaxies revealed their swirling arms. Nebulae glowed with intricate structures of gas and dust. It was like wiping fog off a window that had been clouded for years. Astronomers around the world quickly realized that Hubble could do something very special. It could see incredibly faint objects so distant and dim that they had never been observed clearly before. But that ability came with an interesting challenge. In astronomy, when you want to see something faint, you often need to collect light for a long time. Imagine standing outside at night and trying to see a very distant candle. If you glance quickly in that direction, you might not notice anything at all. But if your eyes have time to adjust and you keep looking carefully, eventually a faint glow might become visible. Telescopes work in a similar way. The longer a telescope observes a particular spot in the sky, the more light it gathers from that area. Even extremely faint objects can slowly build up enough signal to become visible in the final image. This process is called a long exposure. By the early 1990s, astronomers began wondering just how far Hubble could push this technique. What would happen if the telescope stared at one single patch of sky for a very long time? Not minutes, not hours, but days. At first, that might sound like an obvious idea. If you want to see faint things, just keep looking longer. But there was a catch. Time on Hubble was incredibly valuable. Thousands of scientists around the world submitted proposals asking to use the telescope for their research. Some wanted to study planets in our own solar system. Others wanted to observe exploding stars, distant quasars, or swirling nebulae where new stars were forming. Each observation had to be carefully scheduled. Pointing the telescope at a single empty patch of sky for days at a time meant giving up opportunities to study many other targets. So if someone wanted to try such an experiment, they needed a very good reason. Enter an astronomer named Robert Williams. In 1995, Williams was serving as director of the Space Telescope Science Institute, the organisation responsible for managing Hubble's scientific operations. And he had an idea that was both bold and slightly unusual. Williams wondered whether astronomers might be underestimating just how crowded the universe really is. When we look up at the night sky with our eyes, the number of visible stars seems impressive but manageable. A few thousand points of light scattered across the darkness, but telescopes reveal far more. Even a modest backyard telescope can show stars too faint for the naked eye. Larger observatories reveal countless additional objects, and Hubble, with its extraordinary sensitivity, could see even farther. So Williams proposed something simple. Instead of pointing Hubble at a known galaxy, or a star cluster, or any familiar celestial object, what if the telescope simply stared at a region of sky where nothing obvious was visible? No bright stars, no nearby galaxies, just darkness. If the universe truly contained enormous numbers of distant galaxies, then even the emptiest looking patch of sky might still hold secrets waiting to be uncovered. It was a bit like shining a powerful flashlight into a dark forest where, from far away, you thought there were no trees. Once the light reached deep enough, who knew what shapes might appear? Of course, choosing the right patch of sky was important. Astronomers needed a location that was relatively free of bright foreground stars from our own galaxy. Those nearby stars could overwhelm the faint signals from distant galaxies far beyond. After careful consideration, they selected a tiny region in the constellation Ursa Major. If you were to look up at the Big Dipper, that familiar group of stars forming part of Ursa Major, the chosen spot lay not far from its handle. But even if you knew exactly where to look, you would not notice anything special. To the naked eye, that region looked completely empty. No glowing clouds, no star clusters, just darkness. And yet, beginning in December of 1995, Hubble would begin staring into that darkness for 10 straight days. Day after day, orbit after orbit, the telescope pointed its cameras toward that same tiny patch of sky. Each time Hubble circled Earth and passed into darkness on the night side of the planet, its instruments gathered faint light from that distant region of space. Image after image was recorded. Exposure after exposure slowly accumulated. The process required patience. A single short observation would not reveal much. But as the hours turned into days, faint signals began to build up. Tiny specks of light that were invisible at first slowly emerged from the noise. At the beginning of the observation, the images looked almost blank, but with each additional exposure, something subtle began to appear. Faint dots, barely visible smudges, little hints of structure that had never been seen before. Astronomers watched as the data arrived, curious about what the final combined image might reveal. After all, this was supposed to be empty space, at least that's what everyone thought. Yet as the exposures accumulated and the images were stacked together, the darkness began to fill with light. At first, just a few distant shapes, then dozens, then hundreds, and eventually something far more astonishing began to take shape. Because the deeper Hubble looked into that patch of sky, the more objects appeared. Galaxies upon galaxies upon galaxies. Thousands of them, all hidden inside a tiny region of the universe that had once seemed completely empty. And the realization that followed would quietly change the way scientists understood the cosmos itself. At first glance, the patch of sky chosen for Hubble's long observation seemed almost unremarkable. If you stepped outside on a clear night and looked toward the constellation Ursa Major, nothing about that region would catch your attention. No bright star marked the spot. No faint glow hinted at something hidden in the distance. It was simply part of the dark background of the sky, the kind of place astronomers normally ignored because there appeared to be nothing there worth studying, and that was precisely the point. The experiment only worked if the telescope looked somewhere that seemed completely empty. If Hubble had been pointed toward a known galaxy cluster, the results would have been interesting but predictable. Astronomers already knew that galaxies gathered in groups and clusters, and powerful telescopes had observed many of them before. But pointing at a place where nothing obvious existed carried a different kind of curiosity. It asked a much deeper question about the nature of the universe itself. Is the cosmos mostly empty, with galaxies scattered far apart like lonely islands? Or is it packed with distant galaxies too faint for us to notice unless we look very carefully? Answering that question required patience and precision, because the chosen region of sky was incredibly small. In fact, describing just how small it was became one of the most fascinating parts of the story. Astronomers often compare the size of objects in the sky using angles rather than distances. If you stretch your arm out in front of you and hold up your thumb, the width of that thumb covers about 2 degrees of sky. That might not sound like much, but the sky is enormous, stretching in every direction above us. 2 degrees is already a surprisingly large portion when measured in astronomical terms. Now, imagine shrinking that measurement dramatically. The region Hubble observed, which later became known as the Hubble Deep Field, covered an area only about 2.6 arc-minutes across. To put that into perspective, 1 degree is divided into 60 arc-minutes, so the entire deep field area was roughly 1/20th the width of your thumb held at arm's length. Another way astronomers like to explain it is with a grain of sand. Imagine standing outside and holding a tiny grain of sand between your fingers. Stretch your arm out toward the sky and let that grain cover a small patch of darkness above you. The area hidden behind that grain is roughly the same size as the region Hubble studied during its famous observation. That is how small it was. Out of the entire sky, which wraps all the way around Earth like a giant sphere, Hubble was staring at a region no larger than a grain of sand held at arm's length. And yet scientists suspected that even such a tiny window might reveal something extraordinary. The universe, after all, is unimaginably vast. Light travels at about 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second. Even at that speed, reaching the nearest star beyond our Sun takes more than 4 years. Galaxies lie much farther away. The closest large galaxy to the Milky Way, known as Andromeda, is about 2.5 million light-years from Earth. That means the light reaching our eyes from Andromeda tonight actually began its journey toward us long before modern humans existed. But beyond Andromeda lie billions upon billions of other galaxies, scattered across distances that stretch into billions of light-years. When astronomers observe those distant systems, they're not just seeing faraway objects, they're also seeing far back in time. Because light takes time to travel, looking deeper into space is also looking deeper into the past. That simple idea gives telescopes like Hubble a remarkable ability. With enough sensitivity and patience, they can capture light that began its journey billions of years ago, revealing what the universe looked like when it was much younger than it is today. Still, before the deep field observation, many scientists did not fully know what to expect when pointing a telescope into a truly empty patch of sky. Would it reveal a few distant galaxies, perhaps dozens, or maybe nothing at all beyond faint background noise? Even the most optimistic astronomers did not anticipate just how crowded that tiny region of space would turn out to be. Before the long exposure began, the chosen patch looked almost completely dark in previous images. Earlier telescopes had photographed the region and found very little there. That was exactly why it had been selected. Bright nearby stars were avoided because they could overwhelm faint signals from distant galaxies. The team also wanted to stay away from dusty regions of our own Milky Way galaxy, where clouds of gas and dust might block the view of the deeper universe beyond. The selected location offered a clear line of sight out of our galaxy and into intergalactic space. In simple terms, it was like looking through a clean window into the far distance. Once Hubble began its observation, the telescope's cameras captured hundreds of individual exposures over the course of about 10 days. Each exposure gathered faint light from that tiny patch of sky, gradually building a clearer and clearer image as the data accumulated. The process required careful planning. Hubble could not observe continuously because it orbits Earth roughly every 90 minutes. During part of each orbit, the planet itself blocks the telescope's view of the target area. At other times, sunlight reflecting off Earth or entering the telescope's instruments could interfere with the observation. So the telescope gathered data in segments, capturing exposures whenever the chosen patch of sky came back into view during its orbit. Little by little, the exposures added up. Each one captured photons, tiny packets of light that had travelled across unimaginable distances. Some of those photons had begun their journey billions of years earlier, long before Earth even formed. Now they were finally reaching the telescope's mirror. Those photons were incredibly faint by the time they arrived. Many of the galaxies producing them were so distant that their light had spread out across vast regions of space. Only a handful of photons might reach the telescope during a given exposure, but Hubble's instruments were sensitive enough to record them. With every orbit around Earth, the telescope gathered a few more pieces of the cosmic puzzle. As the images were combined, faint structures began to emerge from the darkness. What had once looked like an empty field slowly filled with tiny points and smudges of light. Some appeared as soft elliptical glows. Others showed delicate spiral patterns. A few looked irregular and distorted, hinting at galaxies in the process of forming or colliding. At first, the number of visible objects seemed manageable, but as the exposures grew deeper, more and more galaxies appeared. It was like gradually turning up the brightness on a hidden landscape. Shapes that were invisible before began to reveal themselves. Astronomers realized that nearly every faint speck in the image was not a star from our own galaxy, but an entire galaxy far beyond the Milky Way. Each one contained billions of stars. Each one existed at a different distance from Earth, and each one represented a snapshot of cosmic history, frozen in the light that had travelled across time and space to reach the telescope. The deeper scientists examined the image, the more astonishing the results became. By the time the final composite image was assembled, the tiny patch of sky contained roughly 3,000 visible galaxies. 3,000 galaxies in an area of sky no larger than a grain of sand held at arm's length. That realization quickly led to a staggering implication. If such a small piece of sky contained thousands of galaxies, what about the rest of the universe? The full sky covers an area roughly 40 million times larger than the deep field image. Of course, not every region contains exactly the same number of galaxies, but the numbers suggested something remarkable. If the deep field observation was typical, then the total number of galaxies in the observable universe might reach into the hundreds of billions. Later studies would suggest that the number might even exceed 2 trillion. For a long time, astronomers believed the Milky Way was just one of many galaxies scattered through space. But the deep field observation revealed that the universe might be far more crowded than anyone had previously imagined. And remember, this discovery came from staring at what seemed to be empty space. The darkness between stars turned out not to be empty at all. Instead, it was filled with distant galaxies whose light was simply too faint for earlier instruments to detect. This idea changed how scientists thought about the night sky. When we look up at the stars, most of the points of light we see belong to our own galaxy. The Milky Way contains hundreds of billions of stars, forming a vast spiral system stretching across about 100,000 light-years. But beyond that galaxy lies an even larger cosmic landscape. The galaxies revealed in the deep field image exist far outside the Milky Way, at distances ranging from hundreds of millions to billions of light-years away. Each one represents an enormous collection of stars, planets, gas, dust, and dark matter bound together by gravity. Some of the galaxies in the image appear relatively nearby in cosmic terms, perhaps a few billion light-years away. Others are so distant that their light began travelling toward us when the universe was only a fraction of its current age. The deeper astronomers looked, the further back in time they were seeing. That tiny patch of sky was not just crowded with galaxies, it was also filled with history. Different galaxies appeared at different stages of their development, offering clues about how galaxies form and evolve over billions of years. Some looked mature and well-structured, with graceful spiral arms and bright central bulges. Others appeared smaller, irregular, or chaotic, perhaps representing younger galaxies still assembling themselves through cosmic collisions and mergers. For astronomers, the image became something like a fossil record of the universe. Every faint smudge carried information about the past. Every photon arriving at the telescope told a story that began long ago. Curiosity was certainly part of the motivation behind the deep field observation, but the decision to point Hubble at that quiet patch of sky was not simply an act of cosmic daydreaming. Astronomers had very specific scientific reasons for wanting to look there, and those reasons had been building for decades before the telescope ever began its 10-day stare. To understand the thinking behind it, it helps to remember that astronomers have always been trying to answer a deceptively simple question. How is the universe arranged? Not just nearby space filled with stars, but the entire cosmic landscape. Are galaxies scattered randomly? Do they gather in clusters? How many are there altogether? And perhaps most intriguingly, what did they look like long ago when the universe was young? By the early 1990s, scientists had learned quite a lot about galaxies in the relatively nearby universe. Powerful telescopes on Earth had mapped many millions of them, revealing that galaxies often gather in clusters and superclusters, forming enormous filaments and walls across space. Between those structures lie vast cosmic voids, regions containing far fewer galaxies. Large surveys had begun to sketch the broad architecture of the universe, something astronomers sometimes call the cosmic web. When plotted on large maps, galaxies appear to form a delicate network of threads, stretching across unimaginable distances. But those surveys mostly showed galaxies that were relatively close in cosmic terms. And in astronomy, close can still mean hundreds of millions of light years. The deeper you try to look into space, the harder it becomes to see anything at all. Distant galaxies are incredibly faint, not because they are small or dim, but because their light spreads out as it travels across the expanding universe. Imagine holding a flashlight on one side of a large field and standing far away with a camera. Up close, the beam appears bright and concentrated, But the farther you go, the more the light spreads out and fades. Eventually it becomes so faint that you might not detect it, unless your camera collects light for a very long time. That is exactly the challenge astronomers face when observing the distant universe. Galaxies billions of light years away can still be enormous, containing hundreds of billions of stars, but by the time their light reaches Earth it has weakened dramatically. Detecting them requires patience. It also requires very sensitive instruments. Before the launch of Hubble, most observations of distant galaxies were made with ground-based telescopes. Even the largest of those telescopes struggled with the distortions caused by Earth's atmosphere. Starlight passing through the atmosphere becomes slightly blurred by turbulence. The effect is similar to looking at objects underwater while waves ripple across the surface. The image wobbles and smears just enough to hide extremely faint details. Hubble changed that. Orbiting high above the atmosphere, the telescope could capture much sharper images of distant galaxies than any ground-based observatory at the time. Astronomers quickly realized that this advantage might allow them to push their observations much deeper into space than ever before. Still, a puzzle remained. Even with powerful telescopes, it was difficult to estimate how many galaxies existed in the universe. Surveys had catalogued millions of them, but those surveys covered limited regions of the sky and focused mostly on brighter galaxies. The faintest galaxies, the ones located at the greatest distances, remained largely hidden. Some astronomers suspected that the universe might contain far more galaxies than previously counted. Others wondered whether the number would eventually level off as telescopes reached deeper into space. To settle that question, someone had to perform a very careful measurement. One approach would be to observe many different parts of the sky for short periods of time, building up a statistical picture of galaxy populations. But another approach, perhaps even more revealing, was to stare very deeply into one tiny region and count everything that appeared. That was the idea behind the deep field. If astronomers could measure the number of galaxies in a small, well-defined patch of sky, they could estimate how many might exist across the entire observable universe. It was a bit like counting trees in a small square of forest, and then estimating how many trees might grow across the whole landscape. Of course, that method only works if the sample area is representative, so the chosen region needed to avoid anything unusual. It should not contain a large nearby cluster of galaxies, because that would artificially inflate the count. It should not lie behind thick clouds of dust in our own galaxy, because that dust might hide more distant objects. Ideally, it should simply be a typical slice of the universe. Another reason astronomers wanted to look at such a deep field had to do with time itself. Because light travels at a finite speed, observing distant galaxies allows scientists to see earlier periods in cosmic history. A galaxy 1 billion light-years away appears to us as it looked 1 billion years ago. A galaxy 10 billion light-years away shows us a snapshot from a time when the universe was far younger. That means deep observations act almost like time machines. By studying galaxies at different distances, astronomers can reconstruct how galaxies have changed over billions of years. Before the deep field observation, scientists had some clues about galaxy evolution. They knew that galaxies sometimes collide and merge with one another. They had observed bursts of star formation in certain galaxies and periods of relative calm in others, but many details remained uncertain. What did galaxies look like in the early universe? Were they already shaped into the elegant spirals we see today? Or did they start out as chaotic collections of stars and gas that gradually organized themselves over time? Another mystery involved the rate of star formation in the early universe. Observations suggested that billions of years ago, galaxies were forming stars much more rapidly than they are today. Some galaxies seem to be producing new stars at incredible rates, lighting up the young universe with bursts of energy. But scientists lacked detailed observations of very distant galaxies to confirm how widespread that activity was. A deep observation might reveal thousands of galaxies at different stages of their lives, offering clues about when most stars in the universe were born. There was also interest in something called galaxy morphology, which is simply the study of galaxy shapes. Nearby galaxies fall into several familiar categories. Spiral galaxies, like the Milky Way, contain rotating disks with sweeping arms. Elliptical galaxies appear more rounded or oval, with stars orbiting in less organized patterns. Irregular galaxies lack clear structure and often appear distorted or chaotic. By examining distant galaxies, astronomers hope to learn whether these familiar shapes had always existed, or whether they gradually emerged as galaxies evolved. If very distant galaxies looked messy or irregular, that might suggest that early galaxies were still forming and settling into stable structures. But if they already appeared well organized, it might mean that galaxies matured relatively quickly after the universe began. These questions made the deep field observation far more than just an exercise in counting galaxies. It was an opportunity to study the history of the universe itself. Yet proposing such an experiment still carried a risk. Hubble was a precious scientific instrument with limited observing time. Spending 10 days staring at an apparently empty region of sky could easily be criticized as wasteful if the results turned out to be unremarkable. There was also the possibility that the observation would reveal only a modest number of galaxies, confirming what astronomers already suspected without providing much new insight. But Robert Williams believed the potential reward justified the gamble. If the universe contained far more galaxies than expected, the deep field could reveal them. If distant galaxies looked very different from nearby ones, the images might offer the first clear view of early cosmic history. And if nothing particularly interesting appeared, at least scientists would have tested the idea and learned something about the limits of their instruments. With that reasoning in mind, the plan moved forward. Astronomers carefully selected the patch of sky that Hubble would observe. The region lay in the northern constellation Ursa Major, far from the crowded star fields of the Milky Way's central regions. It was chosen partly because it remained visible to Hubble for extended periods during its orbit, allowing the telescope to accumulate many exposures. The field also avoided bright nearby stars that might overwhelm faint distant objects. In other words, it was intentionally boring, a blank piece of cosmic background. Once the observation began in December 1995, the telescope started collecting light from that quiet region during each available orbit. Cameras captured long exposures through several different filters, allowing scientists to study how galaxies appeared at different wavelengths of light. Over the course of the observation, Hubble recorded hundreds of images that would later be combined into a single deep view. Astronomers knew the process would take time. Each new exposure added only a small amount of information. But with every additional orbit, the faint signals from distant galaxies grew stronger. What began as a nearly empty image slowly filled with points of light, and as the combined picture took shape, the scale of the discovery began to dawn on the scientists watching the data arrive. Because the patch of sky that had seemed empty was anything but empty. It was packed with galaxies, thousands of them, and the deeper Hubble looked, the more of them appeared. That realization made the original motivation behind the observation even more important. Astronomers had hoped to learn whether the universe contained more galaxies than previously estimated. Now they were beginning to see that the answer might be yes. Bold ideas in science sometimes arrive quietly. They do not always begin with dramatic announcements or unanimous excitement. More often they start as a proposal that makes some people pause, tilt their heads slightly, and wonder whether the plan might be a little too unconventional to be worth the effort. The decision to spend 10 days of Hubble's precious observing time staring at what appeared to be an empty patch of sky fell firmly into that category. By the mid-1990s, the Hubble Space Telescope had already become one of the most valuable scientific instruments ever built. Every year, astronomers around the world submitted far more observation proposals than the telescope could possibly accommodate. Committees carefully reviewed those proposals, deciding which projects would receive time on the instrument and which would have to wait, sometimes for years. Each hour of observation carried enormous scientific value. researchers wanted to study exploding supernovae, measure the atmospheres of distant planets, examine the birthplaces of stars inside glowing nebulae, and analyse galaxies billions of light-years away. With so many important investigations competing for attention, dedicating more than a week of continuous observation to a single blank region of sky felt like a gamble. In astronomy, gambles can be exciting, but they also come with consequences. If the Deep Field experiment revealed nothing particularly interesting, critics might argue that valuable telescope time had been wasted. After all, Hubble was designed to investigate specific cosmic objects, not stare into darkness hoping something might appear. The person advocating for the experiment understood those concerns very well. Robert Williams, director of the Space Telescope Science Institute at the time, was responsible for overseeing the scientific operations of the telescope. He had spent decades studying galaxies and understood how revolutionary Hubble's capabilities could be. But he also knew that convincing the scientific community to approve an unusual experiment would require careful reasoning. Williams believed that astronomy had reached an interesting turning point. Earlier generations of telescopes had gradually revealed that the universe contained far more galaxies than people once imagined. In the early 20th century, astronomers were still debating whether the faint spiral nebulae seen in telescopes were part of our own galaxy, or separate island universes scattered throughout space. That debate had been settled in the 1920s, when Edwin Hubble himself demonstrated that some of those nebulae were actually distant galaxies far beyond the Milky Way. Since then, the number of known galaxies had grown dramatically as telescopes improved. By the late 20th century, astronomers knew that galaxies filled the universe in staggering numbers, yet no one had ever tried to measure how densely they populated the deepest regions of space. Most surveys looked for galaxies that were already somewhat visible in earlier images. Observations often focused on regions where interesting objects were known to exist. Williams wondered whether this approach might be biasing the results. If astronomers always pointed their telescopes toward places where galaxies were already visible, they might miss a more fundamental truth about the universe. Perhaps galaxies were hiding everywhere, even in places that looked completely empty. Testing that possibility required a different kind of observation. Instead of chasing known targets, the telescope would simply stare at a small random patch of sky and record everything it could detect. The idea itself was not entirely new. Astronomers had occasionally taken deep exposures of selected regions before, but those earlier observations were limited by the sensitivity of the instruments available at the time. Hubble offered something much more powerful. Orbiting above Earth's atmosphere, the telescope could capture incredibly faint light with extraordinary clarity. Its cameras could record photons that had travelled across billions of years of cosmic history. Still, even with Hubble's capabilities, committing 10 days of observing time to a single blank field remained controversial. 10 days might not sound like a long time in everyday life, but in the world of space telescopes it represented a significant investment. During those 10 days, Hubble would complete roughly 150 orbits around Earth. Each orbit offered an opportunity to observe different celestial targets. That meant the Deep Field project would temporarily replace dozens of other potential observations. Some astronomers worried that the experiment might produce an image filled with noise, perhaps revealing only a handful of extremely faint galaxies that had already been detected in other surveys. If that happened, the project would provide little new insight despite its enormous time commitment. Others were concerned about technical challenges. Long exposures require extremely stable pointing. Even tiny shifts in the telescope's orientation could blur faint objects or introduce distortions into the final image. Hubble's guidance system was excellent, but maintaining precise alignment over hundreds of exposures required careful planning. There were also practical complications related to scheduling. The chosen region of sky needed to remain visible to the telescope during each orbit for as long as possible. Earth itself blocks part of the sky during Hubble's orbit, and bright sunlight can interfere with sensitive instruments. The observing window had to be arranged so the telescope could collect enough uninterrupted exposures to build the deep image. Despite these concerns, Williams believed the potential scientific payoff justified the risk. He also understood something important about exploration. Sometimes the most profound discoveries come from looking where no one has looked before. History offered many examples. When astronomers first aimed radio antennas at the sky in the mid-20th century, they discovered entirely new kinds of cosmic objects, including pulsars and quasars. Those discoveries opened whole new fields of research that had not even existed before. The Deep Field experiment carried a similar spirit of curiosity. Instead of asking the telescope to confirm what scientists already suspected, it would allow the universe to reveal whatever happened to be there. To move the idea forward, Williams proposed using a small portion of director's discretionary time, a special allocation of observing hours that the Institute's director could assign to particularly promising or unusual projects. This approach allowed the deep field observation to bypass the usual proposal competition while still maintaining scientific oversight. Even so, the decision did not come lightly. Astronomers discussed the plan carefully, weighing the risks and benefits. Some remained skeptical, wondering whether the observation would produce anything more than a slightly deeper version of existing galaxy images. Others were intrigued by the possibility that it might uncover something entirely unexpected. Eventually, the project received approval. With the green light secured, the next step involved selecting the exact patch of sky that Hubble would observe. The chosen region needed to satisfy several conditions. It had to lie far from the crowded starfields of the Milky Way, where bright foreground stars could overwhelm faint distant galaxies. It also needed to avoid regions containing large nearby galaxies, or clusters that might dominate the image. Astronomers searched for a location that appeared as empty and unremarkable as possible. After careful analysis, they settled on a small area in the northern sky within the constellation Ursa Major. The region contained very few bright stars and minimal dust from our own galaxy, offering a clear view into the deeper universe beyond. It was, by all appearances, a patch of nothing, exactly what the experiment required. Once the target location was finalized, engineers and scientists began planning the observation sequence. Hubble would capture hundreds of exposures using several different color filters. Each filter allowed the telescope to record light at specific wavelengths, helping astronomers determine the properties of distant galaxies. The exposures would later be combined into a single composite image. This stacking process was essential. Individual exposures might reveal only faint hints of distant objects, but when carefully aligned and merged together, they could produce a remarkably detailed picture. Once the plan was approved and the patch of sky carefully selected, the moment finally arrived for Hubble to begin its quiet experiment. In December of 1995, the telescope turned its attention toward that tiny region in the constellation Ursa Major, a place that had been chosen specifically because nothing obvious appeared to be there. From Earth, the night sky feels enormous. Thousands of stars spread across the darkness, forming patterns people have recognized for thousands of years. But telescopes divide that sky into much smaller pieces. Astronomers often examine individual sections one at a time, studying them with extraordinary precision. In this case, Hubble was about to stare at a piece of sky so small that you could hide it behind a grain of sand held at arm's length, and the telescope would keep looking there for 10 days. Of course, Hubble does not simply sit still in space the way a ground-based telescope might remain fixed in one position during the night. It circles Earth at remarkable speed, travelling roughly 28,000 kilometers per hour. At that velocity, the telescope completes one full orbit around our planet about every 90 minutes. During each orbit, Hubble experiences both daylight and darkness as it moves in and out of Earth's shadow. That constant motion shapes how observations are performed. When the telescope passes over the daylight side of Earth, sunlight can scatter into the instruments and overwhelm the faint signals astronomers are trying to detect. During those times, the telescope typically focuses on targets that are bright enough to withstand the glare, or it waits until conditions improve. But when Hubble moves into Earth's shadow, the sky becomes wonderfully dark. Those periods of orbital night offer ideal conditions for capturing extremely faint light from distant galaxies. The Deep Field observation was carefully designed to take advantage of those moments. Each time the telescope entered darkness during its orbit, its cameras turned toward the chosen patch of sky and began collecting photons. The exposures lasted many minutes at a time, long enough for faint signals to register on the detectors. Then, as Hubble's orbit carried it behind Earth again, the telescope temporarily lost sight of the field. 90 minutes later, the process repeated. Exposure after exposure, orbit after orbit. The plan called for hundreds of these images to be taken over the course of 10 days. Later, scientists would combine them into one incredibly deep view of the universe. But in the beginning, the images looked almost empty. That was expected. When astronomers capture a single exposure of a faint region of space, the signal from distant galaxies is often barely detectable. It can easily be buried beneath background noise from the camera sensors or stray light scattered through the instruments. Think of it like trying to see a distant candle through fog. If you glance quickly, you might notice nothing at all. But if you stare long enough, allowing your eyes to gather more light, the faint glow eventually begins to appear. Hubble worked in much the same way. Each exposure gathered a small number of photons arriving from incredibly distant galaxies. One image alone might reveal only a few faint dots, perhaps even fewer than astronomers hoped for. But the power of the observation lay in patience. Every new exposure added more information. The images were carefully aligned and stacked together using sophisticated computer processing. By combining hundreds of exposures, astronomers could gradually amplify the faint signals from distant galaxies while reducing random noise in the image. Little by little, the darkness began to reveal structure. The first exposures showed only a handful of dim smudges, nothing particularly dramatic. But scientists knew the real picture would emerge only after many exposures were combined. While Hubble continued its steady observation, astronomers on Earth monitored the incoming data. They watched the images accumulate, curious to see what might eventually appear in that supposedly empty region. Even for experienced researchers, there was an element of suspense. After all, the project had been something of a gamble. Some astronomers privately wondered whether the final image might reveal fewer galaxies than expected. Perhaps the deep observation would confirm that the universe really did grow sparse in its most distant regions. Or perhaps something entirely unexpected would appear. Night after night, orbit after orbit, the telescope continued its quiet task. From Hubble's perspective, nothing about the observation was dramatic. The telescope simply held its position with extraordinary precision, tracking the same tiny patch of sky while its cameras recorded faint streams of light. But the photons reaching Hubble during those exposures carried remarkable stories. Some had been travelling for hundreds of millions of years. Others had spent billions of years crossing the expanding universe before finally arriving at the telescope's mirror. Each photon represented a small piece of cosmic history. When those photons struck Hubble's detectors, they were converted into electronic signals and stored as digital images. On their own, the signals were faint and scattered, but when combined across hundreds of exposures, they began forming a much clearer picture. Gradually, the image grew deeper. Objects that were invisible in the early frames began to appear. A faint speck here, another there, then a soft oval glow that hinted at a distant galaxy. Astronomers began noticing something intriguing. The faint points of light scattered across the image were not all the same. Some appeared slightly redder, others bluer. Some had distinct shapes, while others looked more like tiny smudges. These differences suggested that the objects were not stars from our own galaxy. They were galaxies themselves, entire galaxies, each containing billions of stars scattered across the universe and appearing in Hubble's field as delicate flecks of light. The more exposures accumulated, the more of them appeared. Soon the number of visible galaxies grew from dozens to hundreds. Scientists began to realize that the supposedly empty patch of sky was quietly filling with distant worlds. What had once looked like darkness was revealing an extraordinary crowd of galaxies, each one representing an immense cosmic system far beyond the Milky Way. The discovery did not happen all at once. It emerged slowly, exposure by exposure, as the data accumulated. That gradual unfolding made the experience even more remarkable for the researchers watching it happen. With each new image added to the stack, more galaxies became visible. Tiny spirals, faint ellipses, irregular shapes that hinted at galaxies still forming or colliding with their neighbours. Some appeared slightly stretched or distorted, their light bent by gravity as it passed massive objects along the way. Others were so distant that their light had been stretched into redder wavelengths by the expansion of the universe. Astronomers were not just seeing galaxies, they were seeing galaxies from many different eras in cosmic history. Closer galaxies appeared relatively bright and well-defined. More distant ones looked smaller and fainter, their light travelling across billions of years before reaching Hubble. By studying these objects, scientists could effectively look back through time, observing how galaxies appeared at different stages in the universe's evolution. The longer Hubble observed, the deeper that time window became. Eventually, after 10 days of careful observation, the telescope had gathered enough exposures to create the final composite image. Hundreds of frames were aligned and combined, producing a view far deeper than anything previously captured. When astronomers examined the finished image, they were stunned. The tiny patch of sky contained roughly 3,000 galaxies. 3,000! In a region so small it could be hidden behind a grain of sand. That realization carried an astonishing implication. If that small patch contained thousands of galaxies, then the entire sky must contain an almost unimaginable number of them. The universe, it seemed, was far more crowded than anyone had suspected. But the deep field image revealed something even more interesting than the sheer number of galaxies. Each galaxy looked slightly different. Some were large and well-structured. Others were small and irregular. Some glowed brightly with active star formation, while others appeared older and quieter. It was as if the telescope had captured a cosmic museum, displaying galaxies at many different stages of their lives. Astronomers quickly realized that the deep field was more than just a count of distant objects. It was a window into the history of galaxy formation itself. By studying the shapes, colors, and brightness of those galaxies, scientists could begin piecing together how galaxies evolved over billions of years. But before those discoveries could be fully understood, researchers needed to grasp something that made the deep field observation even more astonishing. The patch of sky Hubble had studied was not only small, it was incredibly typical. There was nothing special about it at all, which meant that the thousands of galaxies revealed there might exist everywhere in the universe, hidden in every seemingly empty corner of the night sky. At the beginning of the observation, the images arriving from Hubble did not look particularly exciting. To someone unfamiliar with the project, the early frames might have seemed almost disappointing. The patch of sky appeared mostly dark, with only a few scattered points of light visible across the detectors. But astronomers were not discouraged by that first impression. In fact, they expected it. Deep observations always begin this way. When a telescope captures a single long exposure of a faint region of space, the resulting image often looks sparse and noisy. Tiny variations in the detectors create speckles of brightness, and faint cosmic rays sometimes streak across the frame. The signal from distant galaxies is so weak that it can easily hide among these background patterns. The secret lies in patience. Each exposure gathers only a small amount of information, but when many exposures are carefully combined, the faint signals begin to strengthen while random noise fades away. So when the first few images arrived from Hubble, scientists treated them as the opening pieces of a much larger puzzle. Orbit after orbit, the telescope continued to return to that same quiet patch of sky. Each time it entered Earth's shadow, the cameras opened again and began collecting more light. Exposure number 10. Exposure number 20. Exposure number 50. Gradually, the stacked images began to show subtle changes. A few faint dots appeared that had not been visible before. At first, those dots were so dim that they almost blended into the background. You could easily miss them unless you knew exactly where to look. But when astronomers compared the growing stack of images, the same faint specks kept appearing in the same places. That was the first clue. Random noise would appear in different positions from one exposure to the next. But real astronomical objects remained fixed in the sky. If a faint spot appeared in multiple images at the same location, it was almost certainly something real. Slowly, those repeated signals started to stand out. A tiny glow here, another faint speck there. The first galaxies were beginning to emerge. Each one was incredibly distant. The light reaching Hubble had travelled across billions of kilometres of space, often for billions of years. By the time those photons arrived at the telescope's mirror, they carried only the faintest trace of their original brightness. Yet Hubble was sensitive enough to detect them. The telescope's cameras converted those tiny flashes of light into digital signals, preserving them for later analysis. When the signals from many exposures were added together, the faint dots became clearer. Some appeared as soft circular glows. Others had slightly elongated shapes. A few showed hints of structure that suggested spiral arms or central bulges. Astronomers began examining the growing image with increasing curiosity. The number of visible objects kept rising. With each additional exposure, more dots appeared. What had started as a nearly empty image was slowly filling with distant galaxies. This gradual unveiling was one of the most fascinating aspects of the deep field observation. The discovery did not arrive all at once. Instead, it unfolded step by step, almost like watching stars appear in the evening sky as twilight fades. At first, you notice only the brightest stars. Then, as darkness deepens, more points of light reveal themselves. And if you keep looking long enough, the sky becomes crowded with countless faint stars that were invisible earlier. The deep field worked in much the same way. The longer Hubble stared into that tiny patch of sky, the more galaxies appeared. Researchers working with the data often described a sense of quiet excitement as the image deepened. They knew they were watching something extraordinary develop, even though the changes from one exposure to the next were subtle. One scientist later compared the experience to gradually uncovering a hidden city beneath layers of fog. At first, only a few distant lights become visible, then more appear, revealing streets and buildings. Eventually, the full landscape comes into view. By the time dozens of exposures had been combined, the image contained far more objects than anyone had expected to see in such a small area of sky. Hundreds of galaxies were already visible, and Hubble had not even finished its observation yet. Each new exposure pushed the telescope's vision deeper into space. That depth mattered, because galaxies are not evenly distributed by brightness. The universe contains many faint galaxies that are much harder to detect than the bright ones visible in earlier surveys. Think of it like looking at a distant city at night. From far away, you might see the brightest lights first, perhaps from tall buildings or stadiums. But if your eyes adjust and the air becomes clearer, you start noticing smaller lights from houses, streets and vehicles. Eventually you realize the city contains far more lights than you initially saw. The deep field observation revealed a similar truth about the universe. The bright galaxies were only the beginning. Behind them lay countless dimmer galaxies, each one adding another layer to the cosmic landscape. Some of the newly appearing dots were so faint that they represented galaxies more than 10 billion light-years away. Their light had begun its journey toward Earth when the universe was still young, long before our solar system even existed. That realization added another dimension to the discovery. These faint dots were not only distant in space, they were distant in time. Looking at them was like peering into ancient history. Astronomers carefully studied the colours of these galaxies as they appeared in different filters. Hubble had taken images through several colour bands, allowing scientists to measure how bright each galaxy appeared at different wavelengths of light. Those measurements helped estimate the galaxy's distances. Because the universe is expanding, light travelling across vast distances becomes stretched into longer wavelengths. This effect, known as redshift, causes extremely distant galaxies to appear slightly redder than nearby ones. By analysing the colours of the faint dots in the deep field image, astronomers could identify galaxies located at different points in cosmic history. Some were relatively nearby in astronomical terms, perhaps a few billion light-years away. Others were far more distant, showing us the universe as it looked when it was only a fraction of its current age. The growing image also revealed something surprising about the shapes of those galaxies. Many of them did not look like the neat spirals and smooth ellipticals familiar from observations of nearby galaxies. Instead, some appeared irregular or distorted. A few seemed to be colliding or merging with neighbouring galaxies. Others looked clumpy, as if large pockets of star formation were lighting up different regions of the galaxy at once. These unusual shapes hinted that galaxies in the early universe may have been more chaotic than the ones we see nearby today. Galaxies might have started as smaller systems that gradually merged and grew larger over time. The deep field image was beginning to provide evidence for that idea. But even before scientists could analyse the shapes in detail, the sheer number of galaxies appearing in the image had already become astonishing. By the time the observation was halfway complete, the field was already crowded with distant objects. The supposed emptiness of that region of sky had vanished entirely. Instead of darkness, the image revealed a deep tapestry of galaxies stretching across the cosmos, and the telescope was still gathering more light. Exposure after exposure continued to refine the image, bringing even fainter galaxies into view. Each new layer of data pushed the boundaries of what Hubble could detect. Eventually, as the observation approached its final days, the number of visible galaxies climbed into the thousands. Every tiny speck represented an enormous cosmic system. Billions of stars, countless planets, vast clouds of gas and dust, all packed into distant islands of light scattered across the universe, and all hidden inside a patch of sky that once looked completely empty. Yet one detail about the discovery made it even more astonishing. The deep field observation had examined only a minuscule fraction of the entire sky, a tiny window through which the universe had revealed thousands of galaxies, which raised a very natural question. If that small patch contained so many galaxies, how many might exist across the entire cosmos? At some point during the deep field observation, the mood among the astronomers studying the incoming data began to shift. Early in the project, the images had looked mostly quiet, revealing only a handful of faint objects scattered across the frame. But as more exposures accumulated and the stacked image grew deeper, the number of visible galaxies began rising in a way that was difficult to ignore. What had once appeared to be a nearly empty patch of sky was steadily filling with distant light. Each additional exposure added a little more clarity. Faint dots sharpened into small shapes. Smudges became recognizable structures. And slowly, almost gently, the darkness gave way to a crowded view of the universe. The first time scientists saw the nearly complete image, many of them experienced a moment of disbelief. The patch of sky that had seemed empty now contained thousands of galaxies. Not stars, not noise, entire galaxies. Each one an enormous system containing billions of stars. The final composite image revealed roughly 3,000 galaxies in that tiny field alone. And remember, this was an area of sky no larger than a grain of sand held at arm's length. For astronomers accustomed to looking at relatively sparse images of the distant universe, the result felt astonishing. Before the deep field, scientists certainly knew that galaxies were abundant. Surveys had catalogued millions of them across wide portions of the sky, but those surveys typically focused on brighter galaxies, the ones easier to detect with shorter exposures. The faintest galaxies were often invisible in those observations. Hubble's 10-day stare had changed that. By collecting light for so long, the telescope had pushed its vision far deeper than most previous surveys. And what it revealed was something remarkable. The universe was crowded. Very crowded. Almost every tiny smudge in the image represented a galaxy far beyond the Milky Way. Some appeared as soft oval shapes. Others displayed delicate spiral patterns. A few looked irregular or distorted, hinting at galaxies undergoing dramatic interactions. When astronomers began counting the objects in the field, they realized that galaxies were packed into the image at an astonishing density. Thousands of galaxies in such a small patch meant that the universe likely contained far more galaxies than earlier estimates suggested. To understand why this mattered so much, imagine dividing the sky into millions of tiny squares, each the same size as the deep field. If every square contained roughly the same number of galaxies, then the total number across the entire sky would be enormous. Astronomers performed exactly that calculation. The sky covers about 41,000 square degrees. The deep field represented only a tiny fraction of a single square degree. When researchers scaled up the number of galaxies visible in that patch to the entire sky, the estimated total reached into the hundreds of billions. Later observations and improved models would push that number even higher, suggesting that the observable universe might contain 2 trillion galaxies or more. That is a number so large that it almost loses meaning. 2 trillion galaxies, each one filled with stars, each star potentially surrounded by planets, each planet existing within its own environment somewhere in the vast cosmic landscape. The deep field image offered a glimpse of that enormous population. But the discovery was not just about counting galaxies, it was also about seeing them in extraordinary detail. Because the galaxies in the deep field were located at many different distances from Earth, they represented different moments in cosmic history. Some were relatively nearby in astronomical terms, perhaps a few billion light-years away. Their structures appeared well-formed, with smooth elliptical shapes or clearly defined spiral arms. Others were much farther away. The light from those galaxies had begun travelling toward Earth when the universe was far younger than it is today. In some cases, the galaxies appeared as they were more than 10 billion years ago. Those distant galaxies often looked different. Many appeared smaller and less organised. Instead of graceful spiral arms, they showed irregular clumps of stars and gas. Some looked like fragments merging together, suggesting that early galaxies might have formed through repeated collisions and mergers. The deep field image captured these differences beautifully. It showed galaxies at many stages of development, from chaotic early systems to mature spiral galaxies resembling our own Milky Way. For astronomers studying galaxy evolution, this was an incredible treasure. Instead of relying only on nearby galaxies, they could now examine thousands of galaxies across a vast range of distances. That allowed scientists to study how galaxy shapes, sizes and brightness changed over billions of years. The image also revealed something fascinating about colour. Some galaxies appeared relatively blue, indicating that they contained large numbers of young hot stars. Blue light is produced by stars that burn quickly and brightly, often forming in regions where new stars are being created. Other galaxies looked redder. Redder galaxies tend to contain older stars that burn more slowly. They often represent systems where star formation has slowed or stopped. By analysing the colours of galaxies across the deep field, astronomers could begin tracing the history of star formation in the universe. They discovered that many distant galaxies appeared much bluer than nearby ones. This suggested that the early universe was a far more active place, filled with galaxies producing stars at rapid rates. In other words, billions of years ago, the cosmos may have been a kind of cosmic nursery, with galaxies constantly forming new generations of stars. The deep field image also showed something else that caught astronomers' attention. Some galaxies appeared slightly stretched or curved. At first glance, those distortions might seem like simple irregularities in shape. but in many cases they were caused by a phenomenon known as gravitational lensing. Gravity does not only pull on objects with mass, it also bends the path of light. When light from a distant galaxy passes near a massive object such as another galaxy, or a cluster of galaxies, the gravity of that mass can bend the light's path as it travels through space. The effect is somewhat like a glass lens bending light in a camera. Because of this gravitational bending, distant galaxies sometimes appear magnified, stretched, or duplicated in images. The deep field contains several examples of such distortions, offering valuable clues about the distribution of mass in the universe. These subtle gravitational lenses also helped astronomers detect galaxies that might otherwise have been too faint to see. But perhaps the most profound realization from the deep field came from its simplicity. The telescope had not been pointed at a special region of the sky. It had not targeted a known galaxy cluster or a spectacular nebula. Instead, it had looked at an ordinary patch of darkness, and that patch turned out to contain thousands of galaxies, which meant something important. If galaxies were so abundant in one small area, they were likely abundant everywhere. The empty spaces between stars were not truly empty. They were simply filled with objects too faint for earlier telescopes to detect. The deep field image quietly changed how scientists thought about the night sky. When we look upward with our eyes, we see a handful of bright stars scattered across the darkness. But beyond those stars lies an immense universe filled with galaxies stretching across billions of light years. Each of those galaxies contains billions of stars, and each star might host planets. The night sky, which often appears calm and sparsely populated, is actually hiding a vast cosmic crowd. Hubble's 10-day observation had revealed just how crowded it really was. Yet another realization soon followed. If this tiny patch of sky revealed thousands of galaxies after 10 days of observation, what might appear if telescopes looked even deeper? What if astronomers collected light for weeks instead of days? What if future telescopes with larger mirrors and more sensitive instruments examined similar regions? Would the universe reveal even more galaxies hiding beyond Hubble's reach? One of the most surprising parts of the Hubble Deep Field discovery was not just the number of galaxies it revealed, but the size of the region where those galaxies were found. When astronomers explained the observation to the public, many people imagined that Hubble must have examined a large portion of the sky to uncover so many distant galaxies. In reality, the telescope had looked at an area so small that most people would struggle to notice it at all. Understanding just how small that patch was helps explain why the deep field observation was so astonishing. The image was not showing a special corner of the universe packed with galaxies. It was showing what appeared to be a completely ordinary piece of the sky. To appreciate the scale, it helps to think about the sky the way astronomers measure it. Instead of measuring distances across the sky in kilometers or miles, astronomers use angles. The sky is imagined as a giant sphere surrounding Earth, and positions on that sphere are described using degrees, arc minutes, and arc seconds. If you stretch your arm out in front of you and hold your hand flat, the width of your fist covers roughly 10 degrees of the sky. Your thumb held upright covers about 2 degrees. Those measurements are surprisingly useful when trying to estimate distances between stars or planets while looking upward. But even those familiar measurements are far larger than the area Hubble observed. The full moon, which appears fairly small when you look at it in the sky, spans about half a degree from edge to edge. That means 2 full moons placed side by side would stretch roughly 1 degree across. Now imagine dividing that degree into 60 smaller pieces. Each of those pieces is called an arc minute. The Hubble Deep Field covered an area only about 2.6 arc minutes across. That means the entire field was roughly 1/12 the width of the full moon. Picture the moon in the sky for a moment. Now imagine slicing its face into many tiny squares, each far smaller than the moon itself. One of those little squares would roughly match the region Hubble examined. Another way astronomers like to explain the size involves a grain of sand. If you stand outside at night and hold a small grain of sand between your fingers at arm's length, the tiny area of sky hidden behind that grain is about the same size as the deep field. It is almost unbelievably small. Out of the entire sky surrounding Earth, Hubble studied only that minuscule window, and yet that window revealed thousands of galaxies. The entire sky contains about 41,000 square degrees of area when measured in astronomical terms. The deep field image covered only a tiny fraction of 1 square degree. To put that into perspective, you would need tens of millions of deep field images placed side by side to cover the entire sky. If each of those images contained thousands of galaxies, the total number of galaxies in the observable universe would be staggeringly large. Astronomers quickly realized that this simple scaling exercise had profound implications. Before the deep field observation, scientists estimated that the observable universe might contain roughly 100 billion galaxies. That estimate was based on earlier surveys that could only detect the brighter galaxies within large regions of space. But the deep field image suggested that many galaxies were far fainter than those surveys had revealed. If such faint galaxies were common throughout the sky, then the total number of galaxies might be much larger than previously thought. Later observations using deeper surveys and improved analysis eventually suggested that the number of galaxies in the observable universe might approach 2 trillion. 2 trillion galaxies. That number is difficult to imagine. If you tried to count one galaxy every second, it would take more than 60,000 years to reach 2 trillion. And remember, each galaxy contains billions or even hundreds of billions of stars. Our own galaxy, the Milky Way, is estimated to contain somewhere between 100 billion and 400 billion stars. Many of those stars likely host planets. Multiply that by trillions of galaxies, and the scale of the universe becomes almost impossible to grasp. All of that hidden cosmic population was hinted at by the tiny patch of sky Hubble observed. Another remarkable aspect of the deep field image was how evenly the galaxies seemed to be distributed across the frame. Instead of clustering in one corner or forming a dense group in the center, the galaxies appeared scattered throughout the image. This distribution suggested that the patch of sky Hubble observed was not unusual. It was simply a typical slice of the universe. That idea reinforced a principle that astronomers often refer to as the cosmological principle. The cosmological principle states that, on very large scales, the universe is roughly uniform. No matter where you look, the distribution of galaxies and matter should appear statistically similar. Of course, on smaller scales there are variations. Galaxies gather in clusters, clusters gather in superclusters, and between those structures lie enormous cosmic voids where few galaxies exist. But when viewed across billions of light years, the universe appears fairly consistent. The deep field observation supported that idea. If the telescope had looked at an unusual region containing a giant cluster of galaxies, the results might not have been representative of the universe as a whole. But the even scattering of galaxies in the image suggested that the region was typical, which meant that countless other tiny patches of sky likely contained similar numbers of galaxies. Another interesting detail emerged when astronomers examined the brightness of the galaxies within the deep field. Some were bright enough to show clear shapes and structures. Others were so faint that they appeared only as tiny smudges barely distinguishable from the background. These faint galaxies were particularly important. Their dimness usually indicated that they were extremely distant, meaning their light had travelled across vast stretches of space before reaching Hubble. Many of those galaxies existed billions of years in the past. When scientists analysed the brightness and colour of the faintest galaxies, they realised that some were located more than 10 billion light-years away. That meant the light recorded by Hubble had been travelling toward Earth since the early stages of cosmic history. The deep field image was not simply showing distant galaxies, it was revealing galaxies from different epochs of the universe. Some of the galaxies appeared relatively mature, with well-defined structures resembling those of nearby galaxies. Others looked irregular or fragmented, suggesting that galaxies in the early universe were still forming and evolving. By examining these differences, astronomers could begin reconstructing how galaxies changed over time. The image effectively acted as a kind of timeline. Nearby galaxies represented the universe in its more recent stages. Farther galaxies showed the universe at earlier times, and the faintest galaxies revealed glimpses of the cosmos when it was only a few billion years old. All of that information came from a patch of sky no larger than a grain of sand held at arm's length. When the Deep Field image was first released to the public in 1996, it quickly became one of the most famous astronomical images ever taken. People around the world were fascinated by the idea that such a tiny portion of the sky could contain thousands of galaxies. The image also changed how many people thought about the night sky itself. On a clear night, when you look upward and see stars scattered across the darkness, it can feel as though those stars are isolated points of light separated by vast empty spaces. But the Deep Field observation revealed that beyond those nearby stars lies a universe filled with distant galaxies in every direction. The darkness between stars is not truly empty. It is simply too faint for our eyes to see what lies there. Hubble had provided a way to reveal those hidden structures, and once astronomers understood how small the observed patch truly was, they began to appreciate just how much of the universe remained unseen. Because if one tiny window into the sky revealed thousands of galaxies, imagine what might appear if telescopes looked deeper still, or if they examined many more regions like it. The Deep Field had opened a door. Now scientists wanted to step through that door and explore even more of the hidden universe beyond. By the time astronomers finished assembling the Deep Field image, the first reaction many people had was simple amazement. Thousands of tiny shapes filled the frame. Some looked like spirals, some like faint glowing ovals, and others appeared as small irregular smudges. But the most important realization came when scientists explained what those shapes actually were. They were not stars. They were not clouds of gas. Each one was an entire galaxy. That distinction matters because galaxies are not small objects. They are enormous systems made of stars, gas, dust, and something even more mysterious called dark matter. The Milky Way, the galaxy that contains our solar system, stretches roughly 100,000 light-years across and contains hundreds of billions of stars. Every star you see in the night sky belongs to that same system. When Hubble revealed thousands of galaxies inside that tiny patch of sky, it was essentially showing thousands of systems comparable in scale to our own Milky Way, each one with billions of stars, each one possibly hosting planets, each one representing a vast environment where cosmic events unfold over millions or billions of years. From our vantage point on Earth, however, those immense systems appear incredibly small. Even large galaxies in the Deep Field image are only a few pixels wide. That tiny appearance comes from distance. Most of the galaxies Hubble captured lie billions of light-years away from us. To understand how far that is, it helps to remember what a light-year represents. Light travels at about 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second. Over the course of a year, light travels about 9.46 trillion kilometers, so when astronomers say a galaxy lies 10 billion light-years away, they mean that the light we see today left that galaxy 10 billion years ago. The galaxies in the Deep Field therefore represent incredibly distant parts of the universe. Some of them are relatively nearby in cosmic terms, perhaps 1 or 2 billion light-years away. Others lie much farther back in time, showing the universe as it existed when it was only a few billion years old. But distance is only one part of the story. Astronomers also wanted to understand what kinds of galaxies they were seeing. That meant examining their shapes, brightness, and colours in careful detail. Galaxies generally fall into several broad categories. The first type is the spiral galaxy. Spiral galaxies contain flat rotating disks filled with stars, gas, and dust. Within those disks, long spiral arms sweep outward from the centre, often glowing with regions where new stars are forming. Our own Milky Way belongs to this category, If you could view the Milky Way from far above its disk, you would see a swirling spiral pattern stretching across space. Billions of stars orbit the galactic centre while clouds of gas collapse to form new stars within the arms. Many of the galaxies visible in the deep field display similar spiral shapes, though the details are often faint because of their extreme distance. Another common category is the elliptical galaxy. Elliptical galaxies appear more rounded or oval, lacking the clear spiral arms seen in disk galaxies. Their stars orbit in many different directions rather than forming a flat rotating disk. These galaxies often contain older stars and relatively little gas for forming new ones. Some elliptical galaxies are enormous, containing trillions of stars and dominating the centres of galaxy clusters. In the deep field image, several galaxies appear as smooth glowing ellipses, suggesting they belong to this category. A third type is known as the irregular galaxy. Irregular galaxies lack a clear organised structure. Instead of smooth spirals or rounded shapes, they appear clumpy or distorted. Some irregular galaxies are relatively small systems that never formed stable structures. Others are galaxies in the process of interacting or merging with neighbours. The deep field image contains many irregular shapes, particularly among the more distant galaxies. These irregular structures provide important clues about how galaxies formed and evolved during the early history of the universe. Because the deep field includes galaxies at many different distances, it effectively shows astronomers a range of cosmic ages. Nearby galaxies represent relatively recent stages in the universe's history, while extremely distant galaxies show what galaxies looked like billions of years earlier. One of the most interesting patterns astronomers noticed was that distant galaxies often appeared less organised than nearby ones. Many looked smaller and more chaotic. Instead of elegant spiral arms, they displayed clusters of bright regions scattered unevenly across their shapes. These bright areas likely represent intense bursts of star formation, where large clouds of gas collapse to form new stars. That observation supported an idea that had been developing among astronomers for some time. Galaxies may have formed gradually through a process of growth and mergers. In the early universe, smaller systems of stars and gas likely collided and combined to form larger galaxies. Over time, these systems settled into the organised structures we see today. The deep field provided visual evidence of that process. Some galaxies in the image appear to be interacting with neighbours, their shapes stretched or distorted by gravitational forces. Others look like fragments that may eventually merge into larger galaxies. These interactions play a major role in galaxy evolution. When two galaxies pass near each other, gravity can pull gas and stars into new configurations. Gas clouds may compress, triggering bursts of star formation. Eventually, the galaxies may merge completely, creating a new, larger system. Over billions of years, countless mergers like these have shaped the structure of the universe. The deep field also revealed differences in colour among the galaxies. Colour in astronomy often tells scientists about the types of stars present in a galaxy. Blue galaxies usually contain many young, hot stars. These stars burn brightly but live relatively short lives, meaning blue galaxies are often places where new stars are actively forming. Red galaxies, on the other hand, tend to contain older stars that burn more slowly and emit redder light. Such galaxies may have exhausted much of their gas supply, slowing the formation of new stars. When astronomers examined the deep field, they found many distant galaxies appeared quite blue. That observation suggested that the early universe was full of galaxies producing stars at high rates. Billions of years ago, star formation across the cosmos may have been far more intense than it is today. Another fascinating detail involved the faintest galaxies in the image. Some were so distant that their light had been stretched into redder wavelengths by the expansion of the universe. This effect, called redshift, occurs because space itself expands as the universe grows. As light travels across expanding space, its wavelength becomes stretched, shifting toward the red end of the spectrum. By measuring this redshift, astronomers can estimate how far away a galaxy lies and how long its light has been travelling. Using this technique, scientists determined that some galaxies in the deep field existed when the universe was only a small fraction of its current age. In other words, the image contained galaxies from many different eras. Some formed relatively recently in cosmic history. Others were already shining when the universe was still young. This mixture of distances turned the deep field into something like a historical record. Each galaxy represented a snapshot from a different moment in the evolution of the cosmos. By studying thousands of such snapshots together, astronomers could begin piecing together how galaxies developed over time. The deep field also hinted at something even more intriguing. Some of the faint galaxies might represent early building blocks of larger systems. These small, irregular galaxies may have merged over billions of years to create the massive galaxies we see today. If that idea is correct, then the galaxies filling the deep field are not just distant objects, they are ancestors of galaxies that exist today, ancestors of systems that may one day resemble our own Milky Way. When people first saw the deep field image, many were struck by how beautiful it looked. Thousands of colourful galaxies filled the frame like jewels scattered across velvet. But to astronomers, the image represented something even more powerful. It was evidence that the universe contains an extraordinary number of galaxies, each with its own story, its own stars, and its own place in cosmic history. And yet, all of those galaxies had been hiding inside a patch of sky so small, it once appeared completely empty. When astronomers examined the galaxies in the deep field more carefully, another realization began to sink in. The image was not just a crowded picture of distant galaxies scattered across space. It was something much more unusual. It was also a picture of time. Every object in that image existed at a different moment in the history of the universe. This might sound strange at first, because when we look at ordinary photographs, everything captured in the frame exists at the same moment. A photo of a city street shows cars, buildings, and people all frozen in the same slice of time. Astronomy does not work that way. Light travels at a finite speed, which means it takes time for information about distant objects to reach us. Even though light moves incredibly fast, the distances in space are so vast that the travel time becomes significant. In everyday life, we never notice this effect. When you turn on a lamp across the room, the light reaches your eyes almost instantly. The delay is so small that it feels like no time passes at all. But when we look at objects that are far away in space, the travel time becomes enormous. The Moon, for example, lies about 384,000 kilometers from Earth. Light reflected from its surface takes roughly 1.25 seconds to reach us. When you look at the Moon tonight, you're actually seeing it as it was a little over 1 second ago. That delay is small enough that it hardly matters. The Sun, on the other hand, is much farther away. Sunlight takes about 8 minutes to travel from the Sun to Earth. When you see sunlight streaming through a window, that light left the Sun 8 minutes earlier. If the Sun were to suddenly disappear, which fortunately it will not, Earth would continue receiving sunlight for about 8 minutes before the darkness arrived. Now imagine looking much farther away. The nearest star beyond the Sun lies about 4 light years from Earth. When astronomers observe that star, they are seeing it as it appeared 4 years ago. Galaxies exist at far greater distances. Some of the galaxies in the deep field are billions of light years away. The light captured in Hubble's image began its journey long before human civilization existed. In fact, many of those photons began travelling toward us when Earth itself was still young. That simple fact transforms the deep field into something extraordinary. It is not just a picture of distant galaxies, it is a window into the past. When Hubble looked at galaxies 10 billion light years away, it was seeing them as they existed 10 billion years ago. Those galaxies might have changed dramatically since then, but the light we observe today still carries the image they had at that earlier time. Astronomers often describe telescopes as time machines for this reason. The deeper you look into space, the further back in time you see. The deep field observation pushed that idea to an impressive extreme. Some of the galaxies visible in the image appear relatively nearby in cosmic terms, perhaps 1 or 2 billion light-years away. Their light began travelling toward Earth when simple life was already flourishing on our planet. Other galaxies in the image are much farther away. Their light started its journey when Earth was still forming, when oceans were just beginning to appear on the young planet. And the most distant galaxies in the deep field may represent times when the universe itself was only a few billion years old. To appreciate how remarkable that is, consider the age of the universe. Current measurements suggest the universe is about 13.8 billion years old. That number comes from observations of cosmic expansion, background radiation, and the distribution of galaxies across space. If a galaxy lies 10 billion light-years away, the light we see from it today began travelling toward us when the universe was only around 3.8 billion years old. That means Hubble captured images of galaxies during a much earlier stage of cosmic history. The deep field therefore contains galaxies at many different points along the universe's timeline. Nearby galaxies represent relatively recent chapters. More distant galaxies show us earlier periods. And the faintest, most distant ones offer glimpses of the universe when it was still young. Astronomers often imagine the deep field as a layered view through time. The closest galaxies lie near the front of that view. Behind them are galaxies that existed earlier. Farther still are galaxies from even more ancient times. All of these layers appear in the same image, even though they represent different moments in cosmic history. That arrangement allows scientists to study how galaxies evolved across billions of years. If galaxies in the distant past appear different from nearby galaxies, those differences can reveal how cosmic structures changed over time. And that is exactly what astronomers began noticing when they studied the deep field in detail. The galaxies located closer to Earth often looked familiar. Many had well-defined spiral arms, similar to the Milky Way or the Andromeda Galaxy. Others appeared as smooth elliptical systems containing older populations of stars, but the most distant galaxies often looked different. Instead of neat spiral shapes, they appeared clumpy or irregular. Some seemed small and fragmented. Others showed signs of intense star formation, glowing brightly with young stars. These patterns suggested that galaxies may have undergone significant changes over billions of years. In the early universe, galaxies might have been smaller and less organized. Over time, collisions and mergers between galaxies could have gradually built larger and more stable systems. This process is sometimes called hierarchical formation. Small galaxies form first, then gravity pulls them together into larger systems. Eventually, these systems grow into the massive galaxies we see today. The deep field image provided visual evidence supporting that idea. Another clue came from the colours of distant galaxies. Light from extremely distant galaxies often appears redder than light from nearby ones. Part of this effect comes from redshift, which occurs because the universe is expanding. As space expands, wavelengths of light travelling through it become stretched. Blue light can shift toward green, green toward red, and so on. The farther light travels across the expanding universe, the more its wavelength stretches. By measuring how much the light from a galaxy is shifted toward the red end of the spectrum, astronomers can estimate how far away the galaxy is. The deep field contained many galaxies with strong redshifts, indicating that they were extremely distant. Some of those galaxies were seen at a time when the universe was still forming many of its first large structures. Observing them allowed astronomers to study how galaxies behaved during those early stages. Were they forming stars rapidly? Were they colliding frequently? Were their shapes chaotic or organized? The deep field helped answer many of those questions. In many cases, distant galaxies appeared to be undergoing bursts of star formation. Bright clusters of young stars lit up different regions of those galaxies, producing blue light that stood out in the image. That observation supported the idea that the early universe experienced a period of intense star formation. Billions of years ago, galaxies may have been producing stars much faster than they do today. Over time, as gas supplies were gradually used up or expelled by stellar explosions, star formation slowed. Many modern galaxies now form stars at more moderate rates, but the deep field showed us a glimpse of the universe during a time when galaxies were far more active. Another remarkable aspect of looking so far back in time is that it allows astronomers to trace the development of cosmic structures. The universe did not always look the way it does today. Shortly after the Big Bang, the universe was much simpler. There were no stars, no galaxies, only hot, dense gas slowly expanding and cooling. Over time, gravity caused small regions of that gas to collapse and form the first stars. Those stars gathered into the earliest galaxies. Then galaxies merged, grew larger, and formed the enormous systems we observe today. By looking at galaxies at different distances, astronomers can observe different stages of that process. Nearby galaxies show the mature universe. More distant galaxies reveal earlier phases of development, and extremely distant galaxies show us some of the earlier structures that formed after the universe began. The deep field brought many of those stages together into one remarkable image. Thousands of galaxies, each one representing a different moment in cosmic history, each one contributing another piece to the story of how the universe evolved, and all of them captured within a patch of sky so small that it once appeared completely empty. By the time astronomers finished analysing the first results from the deep field, one thing had become clear. The image was not just revealing distant galaxies, it was revealing something about the earliest chapters of cosmic history. Looking far into space had allowed Hubble to look far back in time, and that meant the deep field was showing galaxies from an era when the universe itself was still relatively young. To appreciate what that means, it helps to step back for a moment and consider the timeline of the universe. Current scientific measurements place the age of the universe at about 13.8 billion years. That number comes from several lines of evidence, including observations of cosmic expansion, the temperature of the cosmic microwave background radiation, and the distribution of galaxies across space. In its earliest moments, the universe looked nothing like the one we see today. Immediately after the Big Bang, the universe was extremely hot and dense. Matter and energy existed in a chaotic state where atoms could not yet form. Everything was packed together in a glowing plasma of particles moving at incredible speeds. For the first few 100,000 years, the universe remained opaque. Light could not travel freely because electrons and protons were constantly colliding with photons. Eventually, as the universe expanded and cooled, electrons combined with protons to form the first atoms of hydrogen and helium. This process allowed light to move freely for the first time. That ancient light still fills the universe today as the cosmic microwave background radiation, a faint glow that scientists can detect in every direction. After that moment, the universe entered a long period sometimes called the Cosmic Dark Ages. During this era, there were still no stars or galaxies. The universe contained vast clouds of hydrogen and helium gas, slowly expanding as gravity worked quietly to gather matter into denser regions. Over millions of years, small fluctuations in density grew stronger. Gravity pulled gas together into clumps that became hotter and denser. Eventually, the first stars ignited. These early stars were very different from the stars we see today. They were often much larger and hotter, burning their nuclear fuel rapidly and ending their lives in powerful explosions. Those explosions spread heavier elements into surrounding space. Elements like carbon, oxygen, and iron, which did not exist immediately after the Big Bang, began to appear for the first time. These elements later became the building blocks for planets, rocky worlds, and eventually life itself. As more stars formed, they began gathering into the earliest galaxies. These first galaxies were probably smaller and less organized than modern ones. They may have looked more like clusters of bright star-forming regions rather than the elegant spirals we see in nearby galaxies today. The deep field observation allowed astronomers to see some of these early galaxies. Because many galaxies in the image lie billions of light-years away, the light reaching Hubble began its journey when the universe was still in those early stages of development. In some cases, the galaxies appear as they existed more than 10 billion years ago. That means Hubble captured images from a time when the universe was less than a third of its current age. When scientists examined the shapes and brightness of these distant galaxies, they noticed something interesting. Many looked small, irregular, and somewhat chaotic. Instead of smooth spiral arms or round elliptical shapes, they often appeared clumpy or uneven. Some looked like several smaller pieces that had not yet fully merged into a single structure. These observations supported an important idea in modern cosmology. Galaxies may have grown gradually through a process of merging and accumulation. In the early universe, smaller galaxies formed first. Over time, gravity caused those smaller systems to collide and combine with one another. Each merger produced a larger and more complex galaxy. This process continued for billions of years. Even today, galaxies still collide and merge occasionally. In fact, our own Milky Way is currently interacting with several smaller neighbouring galaxies. Astronomers also believe that the Milky Way and the nearby Andromeda galaxy will eventually merge billions of years from now. The deep field offered a glimpse of that process during earlier stages. Some galaxies in the image appear distorted, with elongated shapes that suggest gravitational interactions with nearby neighbours. Others look like fragments that may eventually come together to form larger systems. These visual clues help astronomers understand how galaxies evolve over time. Another important discovery from the deep field involves star formation in the early universe. Many distant galaxies in the image appear very blue. In astronomy, blue light often indicates the presence of young hot stars. These stars burn brightly and emit large amounts of blue and ultraviolet radiation. When astronomers see galaxies glowing with blue light, it often means that new stars are forming at high rates. The deep field showed that many galaxies billions of years ago were actively forming stars. This suggests that the early universe was a busy place for stellar creation. Astronomers sometimes refer to a period known as cosmic noon, which occurred roughly 10 billion years ago. During this era, galaxies across the universe were producing stars much more rapidly than they do today. The deep field captured many galaxies from that period. Their bright blue light indicated that star formation was happening across the cosmos at remarkable rates. Over time, as galaxies consumed or expelled their gas supplies, star formation slowed down. Today, many galaxies produce stars more slowly than they did in the past. The deep field helped confirm this pattern. By observing galaxies at different distances, astronomers could compare star formation rates across billions of years of cosmic history. The results showed that the universe has gradually become quieter in terms of star production. Another fascinating aspect of the early universe involves the presence of supermassive black holes. Many galaxies today contain enormous black holes at their centres. These black holes can have masses millions or even billions of times greater than the Sun. In some cases, when gas falls toward these black holes, it releases enormous amounts of energy. The result is a quasar, one of the brightest objects in the universe. Quasars were far more common in the early universe than they are today. Some of the faint points in the deep field are believed to be distant quasars, powered by actively feeding black holes. Observing these objects helps scientists understand how supermassive black holes formed and grew during the early stages of galaxy development. The deep field image also revealed galaxies that appear extremely red. Part of that redness comes from redshift, the stretching of light caused by the expansion of the universe. The farther a galaxy is, the more its light shifts toward longer wavelengths. But in some cases, redness may also indicate galaxies containing older stars, or large amounts of dust that absorb blue light. Studying these red galaxies helps astronomers identify systems that may have formed their stars early, and then evolved more quietly over time. Altogether, the deep field presented a remarkable picture of cosmic history. Nearby galaxies in the image show the universe in its more mature stages. More distant galaxies reveal earlier phases of development, and the faintest galaxies hint at a time when galaxies were still assembling themselves from smaller building blocks. All of these stages appear together in a single photograph. That is what makes deep observation so powerful. Instead of watching galaxies change over billions of years, which would obviously take far longer than any human lifetime, astronomers can look at galaxies located at different distances. Each distance represents a different moment in time. By studying those galaxies together, scientists can reconstruct how the universe evolved. The deep field provided one of the first clear views of that long cosmic story. Take a careful look at the deep field image, and something quickly becomes obvious. The galaxies scattered across that tiny patch of sky do not all look the same. In fact, they appear remarkably diverse. Some are bright and clearly structured, while others are faint and irregular. A few show elegant spirals. Others resemble smooth, glowing ovals. Many look messy or distorted, as if gravity has been pulling them into new shapes. This variety is not accidental. Galaxies come in many forms, and the deep field offered astronomers a rare opportunity to study thousands of them at once. Instead of examining only a few nearby examples, scientists could compare galaxies across vast distances and across billions of years of cosmic history. The result was a detailed snapshot of the many ways galaxies can look and behave. Astronomers have long categorized galaxies into several major types based on their appearance. These classifications were first organized in the early 20th century by Edwin Hubble, the astronomer whose name the famous space telescope now carries. Hubble developed a system often called the tuning fork diagram, which grouped galaxies according to their shapes. Even today, astronomers still use variations of that classification when studying galaxies. One of the most familiar types is the spiral galaxy. Spiral galaxies contain a flat rotating disk of stars, gas, and dust. Within that disk, spiral arms sweep outward from the central region, often forming graceful curved patterns. These arms are not solid structures. Instead, they are regions where gas clouds compress and form new stars. Bright blue stars often light up these arms because newly formed stars burn very hot and emit large amounts of blue light. Our own Milky Way belongs to this category. Although we cannot easily see its shape from inside the galaxy, observations of other spiral galaxies show what the Milky Way likely looks like from afar. A bright central bulge surrounded by a wide disk of stars, with spiral arms curling outward like the arms of a pinwheel. Many spiral galaxies appear in the deep field image. Some are relatively easy to recognize despite their enormous distance. Their spiral patterns remain faint but visible, revealing disks of stars rotating around their centers. These galaxies often appear slightly larger and brighter than many of the smaller smudges surrounding them. That brightness usually indicates they are somewhat close to Earth, compared to the faintest galaxies in the field. Another major category is the elliptical galaxy. Elliptical galaxies look very different from spirals. Instead of flat disks and curved arms, they appear as smooth oval or spherical shapes. Their stars orbit in many different directions rather than following a single rotating disk. Elliptical galaxies often contain older stars and relatively little gas for forming new ones. As a result, they tend to appear redder in colour. Some elliptical galaxies are enormous. The largest ones sit at the centres of galaxy clusters and can contain trillions of stars. Within the deep field image, several galaxies display these rounded shapes. Their smooth appearance suggests that their stars have settled into stable orbits over long periods of time. But the deep field also revealed something more unusual. Many galaxies in the image do not fit neatly into either spiral or elliptical categories. Instead, they appear irregular. Irregular galaxies lack clear structure. Their shapes may look clumpy, stretched, or fragmented. Sometimes this happens because galaxies are interacting with nearby neighbours. Gravitational forces can distort their shapes, pulling streams of stars and gas outward. In other cases, irregular galaxies may simply represent young systems that have not yet settled into organised structures. The deep field contained a surprisingly large number of these irregular shapes. This discovery provided an important clue about the early universe. Many of the irregular galaxies are extremely distant. Because their light has travelled for billions of years, we see them as they appeared long ago. The fact that many of these distant galaxies look chaotic suggests that galaxies in the early universe were still forming and evolving. Over time, repeated mergers and gravitational interactions may have transformed those early irregular systems into the more organised spirals and ellipticals we observe nearby today. Astronomers also noticed that some galaxies in the deep field appeared to be interacting directly with one another. In a few cases, two galaxies seem connected by faint streams of stars and gas. These streams form when gravity pulls material from one galaxy toward another during close encounters. Galactic collisions are actually quite common across cosmic time. Although stars themselves rarely collide during these events, the gravitational interactions can dramatically reshape entire galaxies. Gas clouds may compress, triggering bursts of star formation. Stellar orbits may change, creating new structures. Eventually, the galaxies may merge completely, forming a single larger system. The deep field image captured several galaxies in the midst of these interactions. For astronomers studying galaxy evolution, these examples were extremely valuable. They provided direct evidence that galaxy mergers played a major role in shaping the structures we see in the modern universe. Colour added another layer of information to the deep field. The final image was constructed using several different filters that allowed Hubble to capture light at multiple wavelengths. When these images were combined, galaxies appeared in a range of colours including blue, yellow and red. These colours reveal important clues about the stars within each galaxy. Blue galaxies usually contain large numbers of young, hot stars. These stars emit strong blue and ultraviolet light because of their high temperatures. However, they also burn through their fuel quickly, often lasting only a few million years. When astronomers see a galaxy glowing with blue light, it usually indicates active star formation. Many galaxies in the deep field appear blue, particularly among the more distant objects. This suggests that the early universe contained many galaxies rapidly forming new stars. Red galaxies tell a different story. Their redder colour often indicates older stars that have cooled and evolved over time. These galaxies may have formed most of their stars earlier in their history and now contain relatively little gas for creating new ones. Some red galaxies in the deep field may represent systems that experienced intense star formation early on and later settled into quieter phases. Dust can also influence a galaxy's colour. Large clouds of dust absorb blue light more effectively than red light. When galaxies contain significant amounts of dust, their overall colour can appear redder even if young stars are present. Astronomers must account for this effect when interpreting galaxy colours. Despite these complications, colour remains one of the most useful tools for understanding the life cycles of galaxies. By comparing the colours of thousands of galaxies in the deep field, scientists could trace patterns across cosmic time. They discovered that galaxies in the distant universe often appear bluer, indicating more active star formation. In contrast, many nearby galaxies appear redder and more settled. This pattern supports the idea that the universe experienced a period of intense star formation billions of years ago, sometimes called cosmic noon. During that era, galaxies across the universe were producing stars at rates much higher than today. As time passed, gas supplies gradually diminished and star formation slowed. Another interesting feature of the deep field involved the sizes of galaxies. Some appeared quite large in the image, showing clear structures and bright central regions. Others were extremely small and faint. These small galaxies may represent early building blocks that later merged to form larger systems. In many models of galaxy formation, the universe began with small galaxies that gradually combined through gravitational attraction. Over billions of years, these mergers created the massive galaxies we see today. The deep field provided visual support for that idea. Many of the smallest galaxies appear at very large distances, suggesting they existed early in cosmic history. Meanwhile, larger galaxies appear closer to Earth, representing later stages of galactic growth. One particularly intriguing detail in the deep field involves galaxies that appear distorted into arcs or stretched shapes. In some cases, these distortions occur because the light from distant galaxies has been bent by the gravity of massive objects in the foreground. This effect is known as gravitational lensing. Gravity can bend the path of light travelling through space, much like a glass lens bends light in a camera. When a massive galaxy or cluster lies between Earth and a more distant galaxy, its gravitational field can magnify and distort the background object. Some of the curved shapes in the deep field are examples of this phenomenon. These gravitational lenses are extremely useful for astronomers. They can magnify very distant galaxies, allowing scientists to study objects that might otherwise be too faint to detect. In a sense, gravity itself becomes part of the telescope. All of these shapes, colours and interactions tell a complex story about the universe. Galaxies are not static objects. They grow. They merge. They form stars. They sometimes fade into quieter phases. The deep field image captured thousands of galaxies at different points in those processes. Some appear young and chaotic. Others appear mature and stable. Some are bursting with new stars. Others contain older stellar populations. Together they form a rich tapestry of cosmic history. And all of them were hiding inside a patch of sky that once appeared completely empty. Long before the deep field observation, astronomers already understood that the universe was vast and filled with galaxies. Large telescopes had mapped many regions of the sky, cataloguing millions of galaxies and measuring their distances. Yet those surveys were still limited by how faint an object could be detected during a typical observation. The Hubble Deep Field changed that situation in a very direct way. Instead of surveying large portions of the sky quickly, the telescope had focused all of its attention on one tiny region and simply waited. It collected light for days, allowing extremely faint objects to appear in the image. That simple shift in strategy turned out to have enormous consequences for astronomy. When scientists first examined the completed deep field image, they realized they were looking at something that had never existed before. A truly deep view of the universe filled with galaxies across an enormous range of distances. Thousands of galaxies appeared within that tiny patch of sky. Some were relatively nearby. Others lay so far away that their light had travelled for billions of years before reaching the telescope. For astronomers, this single image immediately opened several new lines of research. The first change involved how scientists estimated the number of galaxies in the universe. Before the deep field, most galaxy counts came from surveys that could only detect brighter galaxies. These surveys covered wide areas of sky but did not look very deeply into space. As a result, astronomers knew about many large galaxies but suspected that numerous faint galaxies remained hidden, beyond the limits of those observations. The deep field provided direct evidence that those faint galaxies were indeed there. Once the galaxies in the image were counted and analysed, scientists realised that earlier estimates had probably been too low. The universe likely contained far more galaxies than previously believed. Later studies combining deep field observations with other surveys eventually suggested that the observable universe might contain roughly 2 trillion galaxies. That revised estimate changed the scale of the cosmos in a very concrete way. Another major impact involved galaxy evolution. Before the deep field, astronomers had already developed theories about how galaxies might form and change over time. These theories suggested that small galaxies could merge together to form larger ones, and that star formation rates may have been higher in the early universe. But testing those ideas required observations of galaxies at different stages of cosmic history. The deep field provided exactly that. Because the image contained galaxies at many different distances, it effectively showed astronomers a timeline of galaxy development. Nearby galaxies represented later stages of evolution. More distant galaxies revealed earlier phases when galaxies were still forming. Scientists could compare shapes, brightness, and colours across this timeline. Those comparisons confirmed that galaxies in the distant past often appeared smaller and more irregular than nearby ones. This observation supported the idea that galaxies gradually grew through mergers and interactions. It also suggested that the early universe was a much more active place for star formation. Another reason the deep field changed astronomy had to do with technology and observation strategies. The success of the project demonstrated that extremely long exposures could reveal structures in the universe that were invisible in shorter observations. That realization encouraged astronomers to design future observations that pushed telescopes to their limits. After the deep field was released, many researchers began planning similar projects using both Hubble and other telescopes. These deeper observations aimed to detect galaxies that were even fainter and farther away. The deep field also changed how astronomers use space telescopes. Hubble had been designed primarily to observe specific objects with great precision. Scientists often targeted individual galaxies, nebulae, or star clusters. But the deep field showed that a telescope could also be used to explore unknown regions of space in search of entirely new discoveries. This idea influenced later observing programs that examined large areas of the sky with extremely sensitive instruments. The deep field also had a powerful effect outside the scientific community. When the image was released to the public in 1996, it quickly became one of the most recognizable astronomical images ever created. People around the world were fascinated by the idea that thousands of galaxies could be hidden inside a patch of sky that once looked empty. The image helped communicate an important truth about the universe. The darkness between stars is not truly empty. It is filled with distant galaxies that our eyes cannot see. That realization gave many people a new appreciation for the scale of the cosmos. Another scientific benefit of the deep field involved measurements of galaxy brightness and color. By studying the light from thousands of galaxies in the image, astronomers could estimate how many stars those galaxies contained and how quickly new stars were forming. These measurements helped scientists build models describing how star formation changed over billions of years. The results suggested that the universe experienced a peak period of star formation roughly 10 billion years ago. During that time, galaxies across the cosmos were producing new stars at much higher rates than today. Since then, star formation has gradually declined. Understanding this trend helps astronomers explain why many galaxies today contain older populations of stars. The deep field also contributed to research involving supermassive black holes. Many galaxies contain enormous black holes at their centers. When gas falls into these black holes, it can release tremendous energy, creating extremely bright objects known as quasars. Some faint points of light in the deep field appear to be distant quasars. Studying these objects helps scientists understand how black holes formed and grew during the early stages of galaxy development. Another important discovery involved gravitational lensing. A few galaxies in the deep field appear stretched or curved because their light has been bent by massive objects located between them and Earth. This effect occurs because gravity can bend the path of light travelling through space. Observing these gravitational lenses allows astronomers to measure the distribution of mass in the universe, including invisible dark matter. The deep field therefore provided valuable data for understanding not only galaxies, but also the large-scale structure of the cosmos. Perhaps the most lasting impact of the deep field was the way it reshaped scientific curiosity. Before this observation, astronomers had many theories about what the distant universe might look like. After the image appeared, they had direct evidence showing that the universe was even richer and more complex than expected. Thousands of galaxies were hiding in a region that once seemed completely empty. Momentum built quickly after astronomers finished studying the original deep field. The image had revealed far more galaxies than anyone expected, and it raised an obvious question within the scientific community. If 10 days of exposure could reveal thousands of galaxies, what would happen if telescopes looked even longer and even deeper? That curiosity led researchers to plan new observations that pushed Hubble far beyond the limits of the first deep field experiment. The original project had demonstrated that long exposures could uncover faint galaxies invisible to earlier surveys. But technology was improving rapidly. and Hubble itself had been upgraded several times through servicing missions carried out by astronauts. New instruments with better detectors had replaced older cameras, allowing the telescope to capture fainter light and record more detailed images. With those improvements in place, astronomers decided it was time to attempt an even deeper look into the universe. One of the first follow-up efforts came in the late 1990s, when scientists conducted another long observation called the Hubble Deep Field South. This project used a similar strategy to the original Deep Field, but targeted a different region of sky in the southern hemisphere. The goal was to confirm that the first deep field had not simply captured an unusual patch of sky. If another deep observation produced similar results, it would strengthen the idea that galaxies filled the universe in every direction. The outcome did exactly that. Thousands of galaxies appeared again, reinforcing the conclusion that the distant universe was densely populated with faint galaxies. But astronomers were still curious about the faintest galaxies of all. Even with 10 days of exposure, Hubble could only detect galaxies down to a certain brightness. Beyond that limit, even more distant galaxies remained hidden. To find those objects, researchers would need to push the telescope even harder. The next major step came in 2004 with the creation of the Hubble Ultra Deep Field. This observation took place in a small region of sky within the constellation Fornax. Astronomers used Hubble's advanced camera for surveys, which had been installed during a servicing mission and offered significantly improved sensitivity compared with earlier instruments. Instead of collecting light for 10 days, the ultra-deep field observation extended for several months. Exposure after exposure was recorded, carefully stacked together to produce the deepest optical image of the universe ever captured at that time. The final image was extraordinary. Roughly 10,000 galaxies appeared in that tiny patch of sky. Some looked familiar, with spiral arms or elliptical shapes similar to galaxies in the nearby universe. Others appeared extremely faint and small, representing galaxies located much farther away. Many of the faintest galaxies were seen at distances exceeding 10 billion light-years. These galaxies existed when the universe was only a few billion years old. For astronomers studying the formation of galaxies, the ultra-deep field offered a remarkable treasure trove of information. It showed that galaxies existed in large numbers even during the early stages of cosmic history. Many of those galaxies appeared small and irregular, supporting the idea that larger galaxies gradually formed through mergers and accumulation. The image also revealed galaxies undergoing intense bursts of star formation. Bright clusters of young stars illuminated portions of those galaxies, suggesting that the early universe experienced periods of rapid stellar creation. One particularly fascinating aspect of the ultra-deep field involved galaxies so distant that their light had been stretched dramatically by cosmic expansion. As the universe expands, wavelengths of light travelling across space become longer. This stretching shifts the light toward the red end of the spectrum, a phenomenon known as redshift. Galaxies with very high redshift appear extremely faint in visible light, because much of their radiation has moved into infrared wavelengths. To detect these galaxies, astronomers began combining Hubble observations with data from other telescopes sensitive to infrared light. This approach allowed scientists to identify some of the most distant galaxies ever observed. But even the ultra-deep field did not represent the final step. Over time, astronomers continued refining the data, adding new exposures from later observations. These additional images extended the depth of the field even further. The combined result eventually became known as the Hubble Extreme Deep Field, often abbreviated as XDF. The XDF project gathered more than a decade of Hubble observations from the same region of sky. By stacking nearly 2,000 individual exposures taken between 2002 and 2012, astronomers produced the deepest image of the universe ever assembled using visible light. The image contained more than 5,000 galaxies within a region of sky smaller than the original deep field. Many of these galaxies were so faint that they appeared as tiny specks barely distinguishable from the background. yet each one represented a massive system containing billions of stars. The XDF allowed scientists to detect galaxies that existed less than 1 billion years after the Big Bang. Observing such distant objects is extremely challenging because their light is incredibly faint and heavily redshifted. Nevertheless, the extreme depth of the image revealed a population of galaxies forming during the earliest stages of cosmic history. These observations provided valuable clues about the period known as cosmic reionization. During the universe's early history, neutral hydrogen gas filled much of space, absorbing ultraviolet radiation from the first stars and galaxies. Over time, intense radiation from these early objects ionized the surrounding hydrogen, allowing light to travel more freely across the universe. Studying extremely distant galaxies helps astronomers understand how that transition occurred. The XDF offered a glimpse of galaxies that may have played a role in reionizing the universe. Another intriguing result from these deeper images involved the number of faint galaxies detected. Each time astronomers pushed the telescope's sensitivity further, additional galaxies appeared. This pattern suggested that many galaxies in the universe remain too faint to detect even with extremely long exposures. In other words, the cosmic inventory of galaxies may still be incomplete. New telescopes with larger mirrors and more advanced instruments will likely reveal even more distant galaxies in the future. The deep field, ultra-deep field, and extreme deep field observations also influenced the design of future space telescopes. Scientists realized that studying the faintest galaxies required instruments capable of observing infrared light, since the light from extremely distant galaxies becomes heavily redshifted. This insight helped guide the development of the James Webb Space Telescope. Unlike Hubble, which focuses primarily on visible light, Webb specializes in infrared observations. Its large mirror and sensitive detectors allow it to study galaxies that formed even earlier than those visible in Hubble's deepest images. In many ways, the Deep Field project served as a stepping stone toward this next generation of cosmic exploration. By demonstrating that long exposures could reveal enormous numbers of faint galaxies, the project changed how astronomers approached observations of the distant universe. It encouraged scientists to look deeper, collect more light, and explore the earlier stages of cosmic history. Today, the deep field images remain some of the most famous photographs ever taken by a space telescope. They remind us that even the smallest patch of sky contains countless galaxies stretching across billions of light years. And they show how a simple idea, pointing a telescope at what appeared to be empty space, can lead to discoveries that reshape our understanding of the universe. Yet these deeper images also highlighted another important question. If galaxies appear in such numbers across the sky, how exactly do telescopes manage to detect objects so faint and distant in the first place? Staring at the deep field image for the first time, it is easy to focus on the galaxies themselves and forget about something equally fascinating behind the scenes. Those thousands of distant galaxies did not simply appear because Hubble happened to be pointed in the right direction. They appeared because the telescope is able to detect incredibly faint signals that human eyes could never see on their own. That ability is one of the most important reasons telescopes exist in the first place. Our eyes are remarkable organs, but they have limits. When we look up at the night sky without any instruments, we can usually see a few thousand stars under very dark conditions. These stars all belong to our own galaxy, the Milky Way. Their light is bright enough to reach our eyes directly. Beyond those stars, however, lies a much larger universe that remains invisible to the naked eye. The reason is simple. Most distant galaxies are far too faint for our eyes to detect. The light from billions of stars spreads out across enormous distances before reaching Earth. By the time that light arrives here, only a tiny fraction of it remains. Our eyes cannot collect enough of those faint photons to form a visible image. Telescopes solve that problem by gathering far more light than the human eye can. The key part of any telescope is its primary mirror or lens. This large surface collects incoming light and focuses it toward a detector. The larger the mirror, the more light it can gather. A useful way to imagine this is by thinking about rain. If you place a small cup outside during a light rainstorm, it will collect only a small amount of water. But if you place a large bucket outside during the same rainstorm, it will collect much more. The same idea applies to telescopes. The pupil of the human eye is only a few millimeters across, even in darkness. A telescope mirror can be meters wide. That enormous difference allows the telescope to collect vastly more light from faint objects in space. Hubble's mirror measures 2.4 meters across. That means it gathers many thousands of times more light than the human eye can. With enough exposure time, it can detect objects that are billions of times fainter than the faintest stars visible to our eyes. But gathering light is only the beginning. Once the telescope collects photons from distant galaxies, it needs a way to record them. Early telescopes relied on photographic plates, which captured images using chemical reactions similar to traditional film. Modern telescopes use electronic detectors called charge-coupled devices, or CCDs. These detectors are incredibly sensitive to light. When a photon strikes the surface of a CCD, it creates a small electrical signal. Millions of these signals are recorded across the detector, forming a digital image. The advantage of CCD detectors is that they can measure extremely faint light with high precision. Each pixel in the detector records how many photons strike it during an exposure. Even if only a few photons arrive from a distant galaxy, the detector can register them. Astronomers can then combine many exposures to build up a clearer image. That process is exactly what Hubble used during the Deep Field observation. Each individual exposure captured only a small number of photons from distant galaxies. But when hundreds of exposures were stacked together, the signals from those galaxies became strong enough to appear clearly. This technique allows telescopes to reveal objects that would otherwise remain hidden. Another important factor in detecting faint galaxies is avoiding interference from Earth's atmosphere. Ground-based telescopes must observe through the atmosphere, which contains moving layers of air that bend and scatter light. This effect causes stars to twinkle and can blur astronomical images. Even small amounts of turbulence can make faint objects harder to detect. Hubble avoids this problem entirely by orbiting above the atmosphere. From its position roughly 540 kilometers above Earth's surface, the telescope enjoys a clear and stable view of space. Light from distant galaxies travels directly to the telescope without being distorted by atmospheric turbulence. This advantage allows Hubble to capture much sharper images than most ground-based telescopes. Still, even with a large mirror and sensitive detectors, telescopes cannot see everything. Many objects in the universe emit light outside the range visible to human eyes. The electromagnetic spectrum includes many types of radiation beyond visible light. These include radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Different astronomical objects produce different kinds of radiation. Cold gas clouds often emit radio waves. Warm dust glows in infrared light. Hot young stars emit strong ultraviolet radiation. Extremely energetic phenomena such as black holes can produce X-rays and gamma rays. To study these different forms of radiation, astronomers use specialized telescopes designed for specific wavelengths. Hubble itself is capable of observing visible light, ultraviolet radiation, and some infrared wavelengths. During the Deep Field observation, scientists used multiple filters to capture images at different wavelengths. Each filter allowed only certain colors of light to reach the detector. By combining images taken through different filters, astronomers could study the colors of galaxies. These colors reveal important information about the galaxy's stars, gas, and dust. For example, galaxies filled with young hot stars appear bluer because those stars emit large amounts of blue and ultraviolet light. Galaxies dominated by older stars tend to appear redder. Dust within galaxies can also change their appearance by absorbing certain wavelengths of light. Another challenge in observing distant galaxies involves something called redshift. As the universe expands, light traveling through space becomes stretched. This stretching increases the wavelength of the light, shifting it toward the red end of the spectrum. The farther a galaxy lies from Earth, the more its light becomes red-shifted. For extremely distant galaxies, light that originally left the galaxy as visible radiation may arrive at Earth as infrared light. This shift means that some galaxies cannot be detected easily using visible light telescopes alone. To observe these galaxies, astronomers must use instruments capable of detecting infrared wavelengths. Hubble's later instruments included infrared detectors that helped scientists study more distant galaxies than earlier cameras could. Other telescopes, such as the James Webb Space Telescope, are specifically designed to observe infrared light. Webb's large mirror and sensitive infrared instruments allow it to detect galaxies that formed during the earliest stages of cosmic history. Another technique astronomers use to study faint objects is gravitational lensing. Earlier we mentioned that gravity can bend the path of light. When a massive object such as a galaxy cluster lies between Earth and a distant galaxy, its gravitational field can act like a lens. This lens bends and magnifies the light from the background galaxy. In some cases, gravitational lensing allows astronomers to see galaxies that would otherwise be too faint to detect. The bending of light can create stretched arcs, rings, or multiple images of the same galaxy. Astronomers carefully analyze these distortions to learn more about both the distant galaxy and the massive object acting as the lens. This technique also provides valuable information about dark matter. Dark matter does not emit or absorb light, making it invisible to telescopes. However, its gravitational influence can still bend light passing nearby. By studying gravitational lensing, astronomers can map the distribution of dark matter in galaxy clusters and across the universe. The Deep Field image contains several examples of galaxies whose light has been distorted by gravitational lensing. These subtle effects provide additional clues about the structure of the cosmos. All of these techniques together allow astronomers to observe objects that would otherwise remain invisible. Large mirrors gather faint light. Sensitive detectors record individual photons. Multiple exposures build stronger signals. Special filters reveal different wavelengths, and gravitational lenses magnify distant objects. When these methods are combined, telescopes can detect galaxies billions of light-years away. The Deep Field observation demonstrated the power of these techniques in a particularly dramatic way. Thousands of galaxies emerged from a region of sky that once appeared completely empty. Those galaxies had always been there, quietly shining across the universe. But until telescopes became sensitive enough to detect their faint light, they remained hidden from view. Understanding how telescopes uncover those hidden galaxies also helps explain why new instruments continue to transform astronomy. Every improvement in mirror size, detector sensitivity, or wavelength coverage allows scientists to see a little farther into space and a little farther back in time. And each time we extend that view, the universe reveals new surprises waiting in the darkness. Consider the emotional impact of seeing the Deep Field image for the first time. Scientists expected to find distant galaxies, but the sheer number revealed something deeper than a catalogue of objects. That tiny square of sky, once thought to contain nothing at all, turned out to hold thousands of galaxies. Each galaxy carried billions of stars, and many of those stars likely hosted planets of their own. That realization gently shifts the way people think about our place in the universe. For much of human history, the night sky appeared simple. Ancient observers saw stars scattered across darkness, perhaps a few thousand visible under the best conditions. Those stars formed familiar patterns called constellations, guiding travelers and inspiring stories across cultures. The universe seemed enormous, yet the visible portion felt manageable, almost intimate. Telescopes slowly changed that perspective. When Galileo first pointed a small telescope toward the Milky Way in the early 17th century, he discovered that the hazy band across the sky was made of countless faint stars. Instead of a cloudy streak, the Milky Way was revealed as a vast swarm of suns. That discovery expanded the scale of the universe dramatically. Later, astronomers realized that our galaxy itself was only one among many. Observations in the early 20th century showed that spiral nebulae were actually distant galaxies far beyond the Milky Way. Suddenly the universe grew again. Instead of one galaxy, there were many. Instead of thousands of stars, there were billions within each galaxy. The deep field observation added another step to that progression. It showed that galaxies fill the universe in astonishing numbers, even in places where nothing seems visible. The empty darkness between stars is not empty at all. It is simply too distant and faint for our eyes to perceive. Inside that tiny patch of sky that Hubble observed, astronomers counted thousands of galaxies, and that patch represented only a minuscule fraction of the entire sky. Once scientists scaled the results across the observable universe, the implications became staggering. The cosmos might contain hundreds of billions or even trillions of galaxies. Each galaxy is an enormous system. Many contain hundreds of billions of stars. Multiply those numbers together, and the total number of stars in the observable universe becomes almost unimaginable. Estimates suggest there may be more stars in the universe than grains of sand on all the beaches of Earth combined. That comparison appears often in astronomy, because it helps people grasp the scale involved. Yet even that analogy struggles to capture the true enormity of the cosmos. Within that vast population of stars, countless planetary systems likely exist. Over the past few decades, astronomers have discovered thousands of exoplanets orbiting stars beyond our Sun. These discoveries suggest that planets are extremely common. Many stars host multiple planets. Some planets orbit within regions where temperatures could allow liquid water to exist. These worlds are scattered across our own galaxy alone. When the deep field revealed that trillions of galaxies might exist across the universe, it quietly expanded the number of potential planetary systems by an extraordinary margin. This does not prove that life exists elsewhere in the cosmos, but it demonstrates that the conditions for planets are widespread. From a scientific perspective, the deep field reinforced an idea that had been developing for centuries. Earth is not located in a special or central place in the universe. This concept is often called the Copernican principle. In the 16th century, Nicholas Copernicus proposed that Earth revolves around the Sun, rather than the other way around. That idea removed Earth from the centre of the solar system. Later discoveries removed the Sun from the centre of the galaxy. Then astronomers learned that the Milky Way itself is just one galaxy among billions. The deep field continued that pattern. It showed that our galaxy occupies only a tiny corner of an immense cosmic landscape filled with galaxies in every direction. In other words, our location in the universe appears fairly ordinary. At first, that realization can feel humbling. Human civilization developed on a small rocky planet orbiting a fairly typical star in a galaxy that is itself one among countless others. Nothing about our location appears particularly special on a cosmic scale. Yet many scientists see this perspective as something inspiring rather than discouraging. Recognizing that the universe is vast encourages curiosity. It invites exploration. It suggests that the processes shaping galaxies, stars, and planets operate across enormous distances and time spans, and it reminds us that the atoms forming our bodies originated in ancient stars. Long before Earth existed, earlier generations of stars produced heavy elements through nuclear fusion. When those stars exploded as supernovae, they scattered those elements across space. Eventually, some of that material gathered into new stars and planets. The carbon in our cells, the oxygen we breathe, and the iron in our blood were all created in those ancient stellar furnaces. In a very real sense, the universe is not just something we observe. It is something we are made of. The deep field image reinforces that connection by revealing the immense environment from which our cosmic story emerged. Each galaxy in that image contains its own history of star formation and stellar evolution. Some may host planets where entirely different environments exist. Most of those galaxies are so distant that their light began travelling toward Earth billions of years ago. That means the deep field does not only show us distant places, it also shows us ancient times. Some galaxies appear in the image as they existed long before the Sun formed. Others represent eras when the universe was still young. Observing these galaxies allows scientists to study how cosmic structures developed over time. But the image also carries a more reflective message. Looking at the deep field reminds us that our daily concerns unfold within a much larger universe. The galaxies filling that tiny square of sky exist at distances measured in billions of light years. Their stars formed and evolved over billions of years. Against that backdrop, the timescales of human history seem brief. Yet the ability to observe and understand the universe is something uniquely human. Through science and technology, people have learned to extend their senses far beyond the limits of the naked eye. Telescopes like Hubble allow us to see galaxies that existed long before humanity appeared on Earth. The deep field is therefore more than just an astronomical photograph. It represents a milestone in humanity's effort to understand the cosmos. From a small planet orbiting a modest star, we have managed to observe galaxies across billions of light years of space. That achievement reflects centuries of curiosity, experimentation, and discovery. It shows how scientific exploration gradually expands our understanding of the universe, and it demonstrates that even the darkest patches of sky contain wonders waiting to be discovered. Yet the deep field also left astronomers with new questions. If the universe contains so many galaxies, could there be even more hiding beyond the reach of Hubble's instruments? Imagine trying to estimate how many trees exist in an enormous forest, while standing at the edge with a small window cut into the trees. Through that window you might see dozens or hundreds of trunks stretching into the distance. You could count the ones you see and then make a rough estimate about how many trees might exist throughout the entire forest. But the deeper the forest goes, the harder it becomes to know whether your estimate is accurate. Astronomers face a similar challenge when they attempt to count galaxies. The observable universe is unimaginably large. Light travels at incredible speed, but even at that speed it can only reach us from a limited region of space, because the universe itself has a finite age. Within that observable region lie countless galaxies scattered across billions of light years. For most of the 20th century, scientists knew that galaxies existed in enormous numbers, but they did not know exactly how many. Early surveys using large telescopes counted galaxies in selected portions of the sky. These surveys revealed millions of galaxies, allowing astronomers to estimate how densely galaxies were distributed across space. By scaling those counts across the full sky, researchers concluded that the observable universe might contain roughly 100 billion galaxies. That estimate seemed reasonable at the time, but those early surveys had an important limitation. They could only detect galaxies bright enough to stand out in relatively short exposures. Fainter galaxies, particularly those located at great distances, often remained invisible. In other words, astronomers were counting only the most obvious members of a much larger cosmic population. The Hubble Deep Field changed that. By staring at a tiny patch of sky for 10 days, Hubble collected far more light than typical surveys had gathered before. The resulting image revealed thousands of galaxies in an area so small it could be hidden behind a grain of sand held at arm's length. That discovery raised a new question. If thousands of galaxies existed in that tiny region, how many more might be hiding in other parts of the sky? To answer that question, astronomers began analysing the deep field data carefully. The first step involved counting the galaxies visible in the image. Researchers identified individual galaxies and measured their brightness, colours, and shapes. Some galaxies appeared relatively bright and easy to recognise. Others were faint smudges barely distinguishable from background noise. Even with Hubble's sensitivity, there were limits to what could be detected. Extremely faint galaxies might still remain hidden in the image. But the number of galaxies already visible was impressive. Roughly 3,000 galaxies appeared in the original deep field, and that was in an area representing only a tiny fraction of the entire sky. Astronomers then performed a simple but powerful calculation. They estimated how many similar patches of sky would fit across the full celestial sphere. If each patch contained a similar number of galaxies, The total count across the observable universe would be enormous. The number suggested that hundreds of billions of galaxies might exist within the region of space we can observe. At first, that estimate seemed astonishing, but further research suggested something even more surprising. Many galaxies in the deep field were extremely faint. Their brightness indicated that they were located at tremendous distances. Some may have been too faint for earlier surveys to detect at all. This meant that previous galaxy counts might have missed a large population of faint galaxies. As astronomers continued studying deep observations from Hubble and other telescopes, they began to revise their estimates. Instead of 100 billion galaxies, the observable universe might contain far more. Later analyses suggested that the number could reach 2 trillion galaxies or more. That revised estimate came from combining data from deep surveys with models describing how galaxy brightness changes with distance. By studying how many faint galaxies appeared in deep images and how brightness decreased with distance, astronomers could estimate how many galaxies likely existed beyond the detection limits of current instruments. The result was a dramatic increase in the estimated number of galaxies. 2 trillion is a number so large that it almost defies comprehension. To put it into perspective, consider our own galaxy again. The Milky Way contains roughly 100 billion to 400 billion stars. Each of those stars is a massive sphere of plasma-burning nuclear fuel for millions or billions of years. Many stars host planetary systems. Thousands of exoplanets have already been discovered within the Milky Way, and scientists believe many more remain undetected. If the observable universe contains trillions of galaxies, each with billions of stars, the total number of stars becomes almost impossible to imagine. Some estimates suggest there may be more stars in the observable universe than grains of sand on every beach on Earth combined, and many of those stars may host planets. The deep field observation therefore had profound implications. It suggested that the universe might be far richer and more populated than earlier estimates had indicated. Yet even these revised numbers come with an important caveat. Astronomers can only observe galaxies within the region of space whose light has had time to reach Earth since the beginning of the universe. This region is known as the observable universe. Beyond that boundary, the universe may continue indefinitely, but light from those regions has not yet reached us. In other words, even the estimate of trillions of galaxies refers only to the portion of the universe we can currently observe. The actual universe could contain far more galaxies beyond our observational horizon. Another factor complicates galaxy counting. Galaxies themselves evolve over time. In the early universe, galaxies were often smaller and less organized. Many of them merged together over billions of years to form larger systems. This means that some faint galaxies seen in deep observations might represent early building blocks of modern galaxies. Several small galaxies in the distant past may eventually merge to form one larger galaxy in the present. Because of this merging process, counting galaxies across cosmic history is not always straightforward. Nevertheless, deep surveys provide valuable insights into the overall population. Each time astronomers push observations deeper, they discover additional faint galaxies. This pattern suggests that the universe contains many more galaxies than we can currently detect. The Hubble Ultra Deep Field and later observations continued this trend. These deeper images revealed thousands of additional galaxies, many extremely faint and distant. Some of the faintest objects detected in these images existed when the universe was only a few 100 million years old. These early galaxies likely played a role in shaping the young universe, contributing to processes such as cosmic reionization. Studying them helps astronomers understand how the first galaxies formed and how they influenced their surroundings. Despite these advances, scientists still believe many galaxies remain hidden beyond the limits of current telescopes. Detecting extremely distant galaxies becomes increasingly difficult because their light grows fainter with distance and shifts into infrared wavelengths due to cosmic expansion. Future telescopes designed to observe infrared light can help overcome this challenge. The James Webb Space Telescope, launched decades after Hubble, was specifically designed to detect faint infrared signals from distant galaxies. With its large mirror and advanced instruments, Webb can observe galaxies that formed earlier in cosmic history than those visible to Hubble. Early observations from Webb have already begun revealing galaxies that existed within the first few 100 million years after the Big Bang. These discoveries suggest that galaxy formation may have begun earlier than scientists once believed. As observations continue, the estimated number of galaxies in the universe may change again. Science rarely provides final answers. Instead, each discovery raises new questions and encourages deeper exploration. The Deep Field observation demonstrated that the universe contains far more galaxies than earlier surveys suggested. But it also reminded astronomers that our current knowledge represents only a snapshot based on the tools available today. New telescopes and improved instruments will likely uncover additional galaxies hidden beyond our present detection limits. In that sense, the Deep Field did not just answer a question about the number of galaxies, it opened the door to an ongoing investigation. How many galaxies truly exist? How early did the first ones form? How did they evolve into the structures we see today? And what new surprises might still be waiting in the darkest corners of the sky? A new chapter in deep space observation began many years after the Hubble Deep Field stunned astronomers. Hubble had revealed thousands of galaxies hiding inside a tiny patch of darkness, and later observations like the Ultra Deep Field pushed that discovery even further. Yet scientists always knew that Hubble had limits. Its mirror, while powerful, measured only 2.4 meters across, and most of its observations focused on visible light. The universe, however, does not reveal all of its secrets in visible light alone. Many of the most distant galaxies shine primarily in infrared wavelengths by the time their light reaches us. Because the universe is expanding, light travelling across billions of light years becomes stretched, shifting toward longer wavelengths. A galaxy that originally emitted bright visible light billions of years ago may now appear mostly in infrared radiation. Hubble could detect some infrared light, but it was not designed to specialize in it. That meant that many extremely distant galaxies remained difficult for Hubble to see clearly. Astronomers therefore began designing a new telescope that could explore this deeper frontier. That telescope became the James Webb Space Telescope. Webb launched in December of 2021 after decades of planning, engineering and testing. Unlike Hubble, which orbits Earth, Webb travels far beyond our planet to a region of space known as the Second Lagrange Point, or L2. This location sits about 1.5 million kilometers from Earth. At L2, Webb orbits the Sun along with Earth, while remaining in a relatively stable gravitational position. This distant orbit allows the telescope to keep its large sunshield permanently facing the Sun, Earth, and Moon, protecting its instruments from heat and light. The sunshield itself is an extraordinary structure. About the size of a tennis court, it consists of multiple layers of reflective material that block sunlight and radiate heat away into space. This protection keeps Webb's instruments extremely cold, which is essential for detecting faint infrared signals from distant galaxies. Heat creates infrared radiation, so a warm telescope would interfere with the delicate measurements Webb is designed to make. Keeping the telescope cold allows its detectors to sense extremely faint infrared light that has travelled across the universe for billions of years. Webb's mirror also represents a significant step forward. Instead of a single, solid mirror like Hubble's, Webb uses 18 hexagonal mirror segments that unfold after launch. Together they form a mirror 6.5 meters across, more than 2.5 times wider than Hubble's mirror. Because a telescope's ability to gather light depends on the size of its mirror, this larger mirror allows Webb to collect far more light from distant galaxies. More light means fainter objects become visible, and faint objects often lie at the greatest distances. When Webb began sending back its first deep images of the universe, astronomers immediately recognized that they were entering a new era of discovery. Some of the earliest observations targeted regions similar to the deep field areas studied by Hubble. These new images revealed galaxies even farther away than those previously observed. Many of the faint red smudges visible in Webb's images turned out to be galaxies that existed only a few 100 million years after the Big Bang. That period represents one of the earliest chapters of cosmic history. Studying galaxies from that era allows astronomers to investigate how the very first galaxies formed. In some cases, Webb detected galaxies that appear surprisingly large and bright for such an early time in the universe. These observations surprised scientists because earlier, theories suggested that galaxies would take longer to grow to significant sizes. Instead, Webb's discoveries suggest that some galaxies form stars rapidly and built large stellar populations earlier than expected. This finding has sparked lively discussions among astronomers. Some researchers propose that early galaxies may have formed stars at much faster rates than models predicted. Others suggest that our understanding of galaxy formation may need adjustments to account for these early massive systems. Either way, Webb is providing data that allows scientists to test and refine their theories. Another remarkable capability of Webb involves spectroscopy. While images reveal what galaxies look like, spectroscopy allows astronomers to analyze the light coming from those galaxies in much greater detail. By splitting light into its component wavelengths, scientists can identify the chemical elements present in distant galaxies. This technique works because different elements absorb and emit light at specific wavelengths. When astronomers examine a galaxy's spectrum, they can detect signatures of hydrogen, oxygen, carbon, and other elements. Studying these signatures helps scientists determine how stars inside those galaxies formed and evolved. Webb's instruments can perform spectroscopy on extremely distant galaxies, providing insight into the chemical composition of the early universe. This information helps answer questions about when heavy elements first appeared and how quickly galaxies enrich their environments with the products of stellar explosions. Another fascinating discovery from Webb involves the shapes of early galaxies. Some appear surprisingly organized, with structures that resemble disks or elongated forms. Others remain irregular and clumpy, reflecting the chaotic conditions of the early universe. Comparing these shapes with those seen in the Hubble Deep Field allows astronomers to trace how galaxies evolved over time. The combination of Hubble and Webb observations effectively creates a timeline stretching from the early universe to the present day. Hubble's images capture galaxies from billions of years ago. Webb extends that timeline further back, revealing galaxies from the universe's first billion years. Together, these telescopes provide a continuous record of cosmic history. Webb has also observed regions where gravitational lensing magnifies extremely distant galaxies. Massive galaxy clusters can bend light from background galaxies, stretching and amplifying their images. This effect acts like a natural telescope, allowing Webb to study galaxies that would otherwise be too faint to detect. Some of the galaxies revealed through gravitational lensing may represent some of the earliest structures ever observed. These observations help astronomers understand how the first galaxies contributed to a process known as cosmic reionization. Earlier we mentioned that the early universe contained large amounts of neutral hydrogen gas that absorbed ultraviolet radiation. At some point, radiation from the first stars and galaxies ionized this hydrogen, making the universe transparent to certain wavelengths of light. The galaxies responsible for this transformation likely formed during the first few 100 million years after the Big Bang. By studying extremely distant galaxies with Webb, astronomers hope to identify the objects that drove this transition. The telescope's ability to detect faint infrared light makes it uniquely suited for this task. Another important area of research involves star formation in the early universe. Webb's instruments can detect warm dust and gas inside galaxies where stars are actively forming. These observations allow scientists to measure star formation rates in galaxies billions of light years away. Understanding these rates helps researchers build models of how galaxies grew over time. Webb's discoveries also highlight the continued importance of deep field observations. Astronomers have already begun creating new deep field images using Webb, similar to the famous Hubble Deep Field but extending into infrared wavelengths. These images reveal even more distant galaxies than Hubble could detect. Some of them appear as faint reddish points barely visible against the darkness of space, yet each one represents an entire galaxy filled with stars. The pattern discovered by Hubble continues with Webb. Every time astronomers look deeper into space, more galaxies appear. The darkness continues to reveal new structures. This pattern suggests that the universe contains vast numbers of galaxies beyond the limits of our current observations. Future telescopes may push these discoveries even further. Plans already exist for next-generation observatories with mirrors larger than Webb's, capable of detecting even fainter signals. These telescopes could reveal galaxies that formed only a few tens of millions of years after the Big Bang. Such observations would allow scientists to study the earliest stages of galaxy formation in unprecedented detail. For now, Webb represents the most powerful space telescope ever built. Its discoveries are still unfolding. Each new observation adds another piece to the puzzle of how galaxies formed and evolved across cosmic time. The Deep Field experiment that began with Hubble demonstrated that even the darkest patches of sky are filled with galaxies. Now Webb is showing us that those galaxies extend even farther back into the universe's earliest history. And with every deeper look into space, astronomers are discovering that the cosmos still holds many secrets waiting quietly in the darkness. Let's return for a moment to that quiet patch of sky where this story began. Not a bright nebula, not a famous galaxy, not even a visible star to guide the eye, just darkness. When astronomers first chose that region for Hubble to observe in 1995, it seemed almost unremarkable. It was selected precisely because it looked empty. The hope was that a long exposure might reveal a few distant galaxies hidden beyond the reach of earlier telescopes. No one expected what actually appeared. After 10 days of patient observation, the darkness filled with thousands of galaxies, spirals, ellipticals, irregular shapes, faint smudges of light that had travelled billions of years before reaching the telescope. Entire galaxies hiding inside a patch of sky no larger than a grain of sand held at arm's length. The discovery changed astronomy in quiet but profound ways. It reminded scientists that the universe is far richer than it appears at first glance. What we see with our eyes represents only the brightest and nearest objects. Beyond those stars stretches an immense cosmic landscape, filled with galaxies in every direction. The Deep Field image revealed that the universe was never truly empty. Even the darkest parts of the sky contain light from distant galaxies. And those galaxies are not just points of light. Each one contains billions of stars. Around many of those stars likely orbit planets, perhaps rocky worlds, gas giants, icy moons, and environments more diverse than we can easily imagine. This realization gently shifts how we think about the night sky. When you step outside on a clear evening and look upward, you see stars scattered across darkness. It might appear as though large portions of the sky are empty space. But the Deep Field showed us something different. That darkness is simply distance. Between the stars, we can see lies an ocean of galaxies too faint and too far away for the human eye to detect. Telescopes reveal them slowly, patiently collecting the light that has travelled across billions of years. The image also carries a subtle reminder about time. Every galaxy in the Deep Field appears as it existed long ago. Some of their light began travelling toward Earth before our solar system formed. Others come from times when the universe was only a few billion years old. Looking at those galaxies is like opening a window into the past. Astronomers often say that telescopes allow us to study cosmic history. Instead of reading about events that happened billions of years ago, we can actually see the light produced during those eras. The Deep Field therefore became more than just a count of galaxies. It became a record of the universe evolving. Some galaxies in the image appear mature and structured, with smooth shapes and well-defined features. Others look small and chaotic, perhaps representing early stages of galaxy formation. Together they form a timeline stretching across billions of years. The Deep Field also reminds us how curiosity drives discovery. The project began with a simple question. What happens if we look at nothing for a long time? That question might sound almost playful, yet it required courage and imagination to pursue. Telescope time is precious, and dedicating 10 days to a seemingly empty region carried risk. But science often advances when researchers are willing to explore the unknown. Instead of pointing Hubble at familiar objects, astronomers allowed the telescope to explore a place that no one had examined in such depth before. The result revealed a universe far more crowded and complex than anyone expected. Since that first deep field observation, astronomers have continued pushing deeper into space. The ultra-deep field and extreme deep field images extended Hubble's reach even further, uncovering galaxies at greater distances and earlier moments in cosmic history. Now the James Webb Space Telescope is expanding that exploration into infrared wavelengths, revealing galaxies that formed during the earliest chapters of the universe. Each new telescope adds another layer to our understanding. Each deeper observation shows that the cosmos contains more structure, more history, and more mystery than we once imagined. Yet the deep field remains special. It was the moment when astronomers realized just how many galaxies might exist beyond our immediate view. A single tiny patch of sky transformed into a vast map of distant worlds. And it all began with darkness. Sometimes discoveries arrive with bright flashes and dramatic events. Exploding stars, colliding galaxies, powerful bursts of energy racing across space. Other discoveries arrive quietly. A telescope points toward an empty region. Light accumulates slowly. Exposure after exposure builds a deeper image, and eventually the universe reveals something unexpected. The deep field was one of those quiet discoveries. It did not involve a sudden explosion or a new object appearing in the sky. Instead, it revealed something that had always been there, waiting patiently to be seen. Thousands of galaxies shining faintly across the darkness. The image also carries a message about perspective. From our everyday viewpoint on Earth, human concerns can feel large and immediate. Cities stretch across landscapes, nations span continents, and our lives unfold within familiar horizons. Yet the deep field reminds us that Earth is part of a much larger environment. Our planet orbits an ordinary star in a galaxy that is itself one among trillions. Beyond the stars, we see each night lies a vast network of galaxies stretching across the observable universe. Understanding that scale can feel humbling, but it can also feel inspiring. Because despite the enormous distances involved, humanity has learned how to explore the universe through observation, mathematics, and technology. From a small planet orbiting a modest star, we have managed to build instruments capable of detecting galaxies billions of light years away. The deep field stands as a symbol of that achievement. It shows what curiosity and careful observation can reveal, and it reminds us that the universe still contains many mysteries waiting to be discovered. Even now, telescopes continue scanning the sky, collecting faint signals from distant galaxies. Future observatories will push these discoveries even further. They will detect galaxies that formed earlier in cosmic history, study the birth of the first stars, and map the large-scale structure of the universe in ever greater detail. The story of the deep field is therefore not just about a single image taken decades ago. It is part of an ongoing journey. Each generation of telescopes looks deeper. Each generation of scientists asks new questions, and each new discovery reveals another layer of the universe. Now, before we finish this quiet journey, let me ask you the same gentle question that often appears at the beginning of our explorations. Where are you listening from tonight? Perhaps it is late where you are, and the sky outside is dark. Perhaps you could step outside and look upward for a moment. The stars you see belong to our own galaxy, but between those stars lies something extraordinary. Hidden galaxies stretching across billions of light years, thousands of them inside every tiny patch of sky, all quietly shining across the vastness of space. The universe was never empty. It only appeared that way until we learned how to look deeper, and somewhere in that immense cosmic landscape, inside one of those galaxies among trillions. You happen to be here right now, listening beneath the same sky that Hubble once stared into so patiently. Sleep well, fellow traveller, wherever you are in this vast universe,